All right, folks, we're back from the break. Up next, we have a talk from Catherine on over-the-air sequential uplink data processing and small-scale cell-free MIMO. You'll probably correct it. Networks. All right, come on up.
Okay. Oh, I think it's a bit high. Can everyone hear me? Okay, perfect. Hi, everyone. Thank you very much for joining me for my talk about over-the-air sequential uplink data processing in small-scale cell-free massive MIMO networks. I know the title sounds a bit dramatic, but I hope it will become clear throughout this presentation. So first, a bit about me. I'm a master's student at KU Leuven, which is a university in Belgium. I'm currently pursuing my master's in electrical engineering with the option of signal processing and information systems. This year, I did my master's thesis in telecommunication, and because of that, got the amazing opportunity to present here. I also want to thank the 6G BRICS project and the Sunrise 6G project, and certainly my promoter, Dr. Sophie Paulin, which provided me the opportunity to be here. So let's start with an introduction. Currently today, mobile networks are implemented in commercial, like the most currently used mobile networks in commercial context are cellular networks. What does this mean? Geographical area where users are located in is divided into different cells. For every cell, there is a base station which serves all the users within that cell. So if I want to send a message with my phone, the base station, which is in the cell which I'm located in, will serve my phone. However, when I go closer to the cell boundary or further from the base station, I will get a worse service due to the larger distance. Also, closer to the cell boundaries, we will have interference from the other cells, which we don't like very much. We don't have these disadvantages in a cell-free network. In a cell-free network, we just throw away the cells and we divide our antennas that were in the base station over different access points, which collaboratively serve all users in the geographical area. That way, we don't have the interference anymore, we don't have the problem anymore that when we go further from the base station that we get a decrease in service. So we have a uniformly good service throughout the area. The cell-free networks were originally introduced in a centralized processing way. So this means that if I want to send a message, for example, to my mom in Belgium, so I send it in the uplink, so I just send it out there, and the access points will receive my signal. They will just forward this to a CPU, and the CPU will perform channel estimation and try to find a signal estimate of the message that I sent. This requires all the access points to be wired to a central CPU and also puts high data rates on the front haul link since the full received signal has to be forwarded to the CPU. If you, for example, think about massive MIMO, there can be a lot of antennas, a lot of signals coming in at the same time, which requires very high data rates. At last, all the computations happen in the CPU. They're not distributed at all. We don't have these disadvantages in a sequential processing architecture. There, the access points are wired sequentially through each other, and at the end of the chain, we have the CPU. In this architecture, the access points still receive my signal that I send in the uplink, but the first AP will find a first signal estimate, forward this together with an error covariance matrix to the second access point, and this will update the signal estimate and try to improve this. This way, the computational load is way more distributed over the different access points, and we have lower data rates on the front haul links. At last, there's also less wiring, which is also very nice. For example, if you think about this conference room, it's way more practical to have like little antennas stick to the wall, and at the end of the chain have a CPU. While if we would have like the antennas and then in the middle a big CPU, would not be practical. For example, if you think about a stadium or a train station as well, this is a way better architecture. There are, of course, disadvantages. For example, the delay when you go to this chain, but also a quantization error that can build up throughout it. It has been shown in theory that if we're using a Kalman-based mean squared error optimal sequential linear processing algorithm, we can actually obtain the same signal estimate after the sequential chain as we could in the centralized processing architecture if we have unlimited capacity on our front haul links. This means we could obtain the same performance in terms of spectral efficiency. So my question in my thesis was, what are the effects of over-the-air transmission and processing on this result? Or the research question, how does sequential uplink signal processing perform using real-world transmission and processing? That includes a wireless channel as well as the receiver front end of the radio, but also synchronization issues, measured channel statistics, and front haul limitations. My steps for achieving this goal or answering my research question were to first research and extend the existing OFDM implementation between two Pluto SDRs in radio, and after that set up a small-scale cell-free massive MIMO network with both sequential and centralized architecture to compare both of them. So I'll quickly go over the two steps. Let's first start with the OFDM link. The OFDM transmitter that was existing already in radio is actually pretty good, and I could fully copy it into my implementation. What I did was I extended it with an easy configuration for multiple user configurations. So as was told also in the last talk, we have OFDM, and in this OFDM we have a lot of subcarriers. We use some of them for channel estimation, some of them for data transmission, and if we have more than one user, we have to assign the different subcarriers to the different users, and I automated this. So I implemented an automatic spectrum divisioning into coherency blocks where you expect the channel to behave more or less stable. And this method takes as input parameters the fast Fourier transform size, the active subcarrier spacing, the number of users, and the guard bandwidth at the ends of the spectrum, and automatically gives this pilot subcarrier indices, data subcarrier indices, and pilot symbols, which can then be used in the existing new radio block. I did implement my own OFDM receiver. The existing open source implementation did not allow for LMMSE channel and signal estimation, so this is linear minimum mean squared error channel and signal estimation, which is needed to have optimal performance. It did also not allow for easy extensions to multiple access points and multiple user architectures, and also not for sequential signal processing. So I implemented my own receiver with the custom Python blocks in your radio to solve for these shortcomings. The main ones are shown there. So we have the channel estimation block, the signal estimation block, which performs optimal sequential linear processing, and the signal estimation one, that's the centralized block. Now that we have a fully working OFDM link, I could set up a small-scale cell-free massive MIMO network. The target configuration was to have 2 users and 2 access points, which is shown here for the sequential architecture. So the 2 users send their data in the uplink. The access points receive the superposition of what they have sent. The first access point will try to find a channel estimate for the channel between itself and the 2 users and find a signal estimate, and then forward this to the second access point, which will update these signal estimates and send this to the CPU. This is the GNU radio flow graph for one access point. So in orange, you see the OFDM demodulation. In blue, there's a channel estimation part. The signal estimation is shown in green, and then the darker blue part is used for forwarding to the next access point, which is an identical flow graph. I hope these are gonna work. So this is what it looks like in the first access point. So we have the channel estimates in the top left, and right there's a received OFDM spectrum. I sent QAM4 symbols, but they're not yet visible in the signal estimate, as is logical, as we have 1 access point and 2 users, so we cannot distinguish between what they sent yet. In the second access point, the signal estimates are updated, and we can clearly see the QAM4 symbols coming out. The target configuration for the centralized architecture also contained 2 users, 2 access points to be able to compare them. In this architecture, the 2 users again center uplink data. The access points receive it, forward this to the CPU, where both channel and signal estimation happens. This is one flow graph, since we don't have the sequential architecture. Again, we see in orange the OFDM demodulation, in blue the channel estimation, and in green the signal estimation. If you have any questions about the flow graphs or after, you can just come up and ask them to me. And then here we see right from the start, since we only have one step, that we immediately obtain the QAM4 symbols. So the result was actually 100% accuracy of the transmission after data detection, but that's not what we were interested in. We were interested in the difference between the centralized and the sequential processing, and they were the same up to a discrepancy of the order of 10 to the minus third, which is probably due to a numerical error because of the rounding in GNU radio. That brings me to the conclusion. So I extended GNU radio's OFDM link between 2 Pluto SERs to allow for LMMSE channel and signal estimation, reconfiguration to multiple users, multiple access points, and massive MIMO, and sequential architectures, and I built a small-scale, cell-free massive MIMO network. Those allowed me to evaluate sequential uplink signal processing using over-the-air transmission and signal processing, and confirmed the results up to a discrepancy of 10 to the minus third. Of course, there were lots of limitations to my work. As I told you, the disadvantages of sequential processing are the delay and the quantization. I used a post-processing approach, so I didn't really have like the downside of the delay, and also the quantization remained very limited, so I didn't see that. On the other hand, the project remained very small scale, even though I tried to make a very modular implementation in the radio. I only tested it with 2 users, 2 access points, and we didn't have a realistic multipath fading environment, since the Plutos both had to be wired to my laptop, so I couldn't place them in a realistic environment. So in future work, I would like to first do some synchronization enhancements, since I had some phase offset because of the Plutos, but also I would like to add more realistic front haul limitations, do an extension to more antennas to have like a more massive MIMO context, more access points, more users, and in the end I would like to add a multipath fading environment, or try to at least. That's all. Thank you very much for listening.
Thank you very much. We have about time for maybe one question. Does anyone in the audience have any questions? Oh, hold on one second.
Thank you for the information, Kat. Very useful. Could you tell me maybe a little bit about the challenges that you faced while making your own blocks in GNU Radio?
The challenges?
Yeah, for the channel estimation blocks, what do you think was the...
So I conquered a lot. So I had both time synchronization, frequency synchronization, and distortion that were happening at the same time. I had never worked with Pluto SERs before, so I didn't know a lot about practical challenges, or I had never had frequency offset before. So like having those 3 all at once was tough, but figured my way out. But I think, yeah, it was, I didn't know anything about OFDM before I started this. I didn't know anything about mobile networks. I didn't know anything about implementation. So I think it was just all new information. Yeah, but yeah, that was about it.
Thank you.
All right, let's give a round of applause for Catherine. Thank you very much.
Very much.
Up next, we have Christopher Long. Okay, Christopher will be presenting on hardware in the loop simulation with PYNQ for radar applications. All right.
Hey, good morning, everyone. My name is Christopher Long. I'm a scientist at the Naval Information Warfare Center Atlantic, which is a warfare center located in Charleston, South Carolina. Over the past year, I've been working in radar-related research, and since then, we've developed a workflow to help us to rapidly prototype algorithms for radar applications. And we thought it would be of interest to the GNU radio community, and so I'm here to present on that today. So this work seeks to rapidly prototype and validate algorithms for radar applications using a hardware-in-the-loop approach and the PINK framework. The algorithm we'll be validating in today's presentation is the cross-ambiguity function, and we will be accelerating this on the FPGA board, which will be our hardware-in-the-loop. Additionally, we'll use GNU radio to handle sending signal data to our FPGA board and then taking the data out of the FPGA board to display and visualize in GNU radio. These slides will also provide relevant background information on core topics to this presentation. And also, if you enjoy this presentation, I'd recommend that you please check out our paper on the same topic. So going on to our agenda for today, first we'll cover those core background topics to this presentation. Then we'll go through our workflow, starting with how we prototyped in Python and then integrated into GNU radio. We'll then discuss how we generated our signals for testing, specifically the transmit and receive signals. And then finally, we'll end on results, conclusions, and final thoughts. So with that being said, we'll start with our first piece of background, which will be hardware-in-the-loop. So hardware-in-the-loop is a simulation technique used to validate hardware performance by connecting your piece of hardware to a software simulated environment. You can see our example here on the right-hand side. This is our setup where we have this PINK FPGA board on the left side of the photo, connected to our developer laptop, which is sending it recorded signal data. The FPGA is processing the data and then returning it to be viewed in GNU radio. Benefits of using this type of approach, it helps to reduce cost and time of development since you don't have to go out into the field every time you have to test your system. It also helps to prevent late-stage fixes since you're able to catch these bugs and discrepancies early on into the development cycle. And finally, it also helps to be able to test in a controlled and reproducible environment. So all these tools help to make hardware-in-the-loop a very valuable resource for rapid prototyping. The next bit of background that we'll cover is the cross-ambiguity function. Again, this is the algorithm that we'll be accelerating on the FPGA board today. So this is an algorithm that allows us to compare two signals. Actually, if you look at our radar scenario at the bottom left-hand corner of this slide, you can see these two signals that we'll be using. So the first is our transmit signal. This is the signal leaving our radar system and going towards our target, which in this scenario is a plane. We'll be comparing that against our receive signal, the red signal bouncing off the plane and coming back to our radar system. And by comparing these two signals, we'll be able to estimate the distance and the velocity of the targets, and we'll do this by comparing the two signals at different time intervals. This will help us to know the delay between the receive and the transmit signal, and from that we can deduce the distance of the target. And we'll also be comparing the two signals at different frequency shifts to figure out the velocity due to the Doppler shift effect, right? So if the target is moving towards us, then the receive signal is going to come back at a higher frequency than the transmit signal, and if the target is moving away from us, then the receive signal will of course be a lower frequency than the transmit signal. The output of the cross-ambiguity function is a 2D matrix, and we can plot this 2D matrix as a range Doppler map. You can see on the bottom right-hand corner of this slide. So to read this map, targets appear as peaks in this plot, circle 1 in red here. The y-axis is the range, so the higher a target is on the map, the farther away it is. And the x-axis is the Doppler shift. So if a target's in the dead center, it is neither moving towards us or away from us. If it's on the right side, that indicates a positive Doppler shift, so the target is approaching us. And if it's on the left side, then that means a negative Doppler shift, so the target is moving away from us. So to summarize the cross-ambiguity function, we'll compare these two signals, transmit and receive, and be able to plot as a range Doppler map to be able to visualize this useful data. We'll also use FFTs, fast Fourier transforms, in our implementation. This is very commonly used to help speed up the processing of cross-ambiguity. Our next bit of background is FPGAs, also known as field programmable gate arrays. These are essentially chips that can be programmed and reprogrammed into different custom digital circuits. One of the main benefits of using this type of hardware, it helps to enable hardware acceleration. since we're able to implement our algorithm on digital logic rather than having to run it on a general purpose processor such as a CPU. Additionally, it gives us deterministic timing, so we know down to the clock cycle how long a specific operation will take, which can be very useful in certain scenarios. You can find this hardware in very common fields such as telecommunications, healthcare, finance, and of course aerospace and defense. Within defense, you see FPGAs commonly used in electronic warfare, sonar, and of course radar, and really any application that uses digital signal processing. The line of chip that we'll be using for our experimentation is the Zinc system-on-chip, which is a line of chips produced by Xilinx. System-on-chips means that we're going to combine that custom digital fabric from the FPGA with an ARM processor, typically running some form of Linux, which really kind of gives us the best of both worlds, where we're able to make these standalone devices with an operating system and a CPU, but also has access to this fabric that can be used for hardware accelerated purposes. And the final piece of background that we'll cover is PINK. So PINK is Python productivity for Zinc, that line of chip that we're using in today's presentation. This is an open source project developed also by Xilinx and allows us to be able to control FPGA hardware using common Python APIs, all from a Jupyter notebook. Under the hood, it's actually Ubuntu running on the ARM processor for PINK, and it includes packages for Jupyter Notebook and common Python libraries such as NumPy, Matplotlib, PyTorch. Really, if it's a common Python library, it's probably included within the package. And it's really great for rapid prototyping since it helps to abstract the communication between the processing system and your FPGA implementations. It also makes it a bit easier to implement and integrate into existing Python applications since all of it's already in Python. So now that we've covered the core background topics, I'm going to give a quick overview of our workflow, and then we'll go through the workflow step by step in the following slides. So first, we prototype our implementation in Python. We then implement our algorithm on an FPGA using, in our case, Vitis HLS. We then integrate our FPGA implementation into our hardware-in-the-loop system. And then finally, we'll use GNU radio to handle sending data to our FPGA and then receiving it back and displaying the results. So starting with that first bit of the workflow, Python prototyping. So really, the main goal of this stage is to get a working proof of concept off the ground to make sure your implementation's working as you expect it to. So what we did was we used NumPy to generate signals, our test and receive signals for initial testing. We then implemented cross ambiguity in Python, and then we used Matplotlib to plot it as a range Doppler map, which you can see on the right-hand side here. We don't include any code in this presentation. However, if you're interested in seeing our Python implementation for cross ambiguity, please check out our paper. We do include a snippet in that. But this stage is really helpful for us validating your implementation and making sure it works as you expect it to. We'll also use our Python prototype to also validate our FPGA implementation a couple stages from now. Next is Vitis HLS. So we use this tool to implement our FPGA block. Feel free, if you're an FPGA developer, to use whatever method you feel most comfortable with, whether it's HDL or some other type of HDL generator. But for this, we use Vitis HLS. So Vitis HLS is used to, you can write your algorithm in C++, and then it converts that down into a FPGA block that can then be ran on the fabric, and so they can take advantage of that hardware acceleration. In our implementation, we use directives to specify pipelining and also specify data flow. And we also use Xilinx's pre-made FFT block in order to help speed up the computation. So the main thing to get away from this slide is that we implement our algorithm, and we have, the end result is this block at the bottom right of the slide that can now run on the FPGA fabric. In the next slide, we need to connect it to our processing system. So if you're unfamiliar with Vivado, this might look like a lot. We'll break it down. So towards the top right, you'll see that block we generated in the previous slide, the cross ambiguity block. And we're just trying to connect that to our processing system on the very right. There's these AXI interconnects in between and on the very far right, or left side. Those are just, you can just think of those as helpers to help connect the two systems. And in the very bottom left, you can see our processing system reset. We won't use that directly, but it's used for resetting the system as needed. And it's good to know that's there. But again, the main idea is just that we're connecting our FPGA core here to the processing system. On the next slide, we'll look at a more abstract representation of this, where we have that ARM processor, that processing system, running Pink. And then we'll use Pink to communicate with our cross-ambiguity implementation on the FPGA fabric, where the red and blue arrows are these two signals, transmit and receive, and that purplish pink color is the cross-ambiguity output, that 2D matrix. So once we have that integrated and working, we'll replace our previous Python implementation of cross-ambiguity with our new and improved FPGA implementation of cross-ambiguity. So we'll use the same NumPy signals that we generated a couple of slides ago. We'll pass that into our FPGA for processing and reuse matplotlib to plot the output. So on this slide, we'll see the two outputs and compare them. So we have our Python on the left here, FPGA output on the right. Generally, it's a good thing if they look similar. However, if they don't, it's a good way to catch discrepancies and any errors early on into the development cycle. So that is our arranged Doppler output using the FPGA. So moving forward, we're going to talk about how we integrated this into GNU Radio. So on the right side here, you can see again that more abstract representation of the connection here. So we stood up and developed a UDP server running in Python on the FPGA board, that processing system. And then we wrote a cross-ambiguity client block. Under the hood, it's a embedded Python block. And the main purpose it serves is to pass signal data, the receive and transmit signals from GNU Radio to our FPGA board over an Ethernet connection. And then we return back that cross-ambiguity output back over the Ethernet connection to GNU Radio. So next we'll see what this looks like in its complete context in our cross-ambiguity flowchart. So we'll break this down going from the very left, working our way to the right. So on the left-hand side, the red and the blue boxes are our signals. Those are recorded signals saved to a text file. Red again being our receive, blue being our transmit. We'll then throttle our reads from those down to our desired sample rate, which in this case is 40 kilohertz. We'll then do two things to the signals. So on the outer side of the flow diagram, we have our Qt GUI time sync, just so that we can visualize our signals in the time domain in real time. And then we'll convert these signals using the stream to vector to a vector in order to prepare it for cross-ambiguity. We'll then hand those off to the cross-ambiguity client, which will then offload that computation to the FPGA. The FPGA will return the output. We'll pass that to the log10 GNU Radio block. This is just to convert the matrix to a logarithmic scale, just make it easier to view and plot. And then we'll finally pass it on to the Qt GUI matrix sync to visualize our range Doppler map. So now that we have that all together, that is our cross-ambiguity flowchart, we're going to look at how we generated our signals for testing. And we'll start with the transit signal. So a very simple approach. We used an RTL SDR to capture a local FM radio station. And we took that signal from the station and we passed it through a low-pass filter. And then we decimated it down to our desired sampling rate, which was 40 kilohertz. And we then saved that to a text file and also to pass into a GUI sync to view as well. So this will be our transit signal for cross-ambiguity. And it will also save or serve as our the base for our reference or the receive signal. So we'll edit the signal in order to make it look like it bounced off of a moving target. So our receive signal, we're going to break this up into a few slides. So this is the first of three. We're just going to read from the transmit signal text file again, throttle that down to 40 kilohertz, convert that to a vector in preparation for the next couple of slides, and then pass that on to stage 2, where we will create two types of signals. So the first type of signal on the upper half of the slides is the target signal, and we use two embedded Python blocks to modify the signal. The goal of the signal is just to make it simulate the transmit signal bouncing off of a moving target. So the first block we implemented was a swirling model. A swirling model is a statistical model used to describe how the amplitude of a signal fluctuates over time due to reflecting off of a moving target. So we implemented that as a block, and then our next block is the delay and frequency shift block, which adds a delay to the signal, simulating the time it takes for the signal to bounce off and return to our station. And then it also adds a frequency shift to the block to simulate the Doppler shift effect occurring by bouncing off of a moving target. We then use a fast multiply const block just to be able to adjust the amplitude as needed in our design. And then we pass that on to stage 3. Next, we're going to talk about the clutter signal, which is on the bottom half of this slide. So clutter is unwanted echoes that are reflecting off of objects that are not targets of interest. So things like trees or buildings, really anything where we're sending out a transient signal and it's unwantingly sending that signal back at us. So to do this, we reused our delay and frequency shift block from the target signal. We just set this frequency shift to 0 to indicate that this is stationary clutter, it's not moving. So it wouldn't give the signal a Doppler shift. And then we set the delay to various amounts, whatever you want. Just make it different distances from the transmitter, per se, in this sim. And then we pass those two onto the third stage, where we'll add all 3 signals together. We'll do one last fast multiply const to adjust the amplitude one last time, convert the final vector to a stream, and then we'll save that as our received signal for this scenario. So that concludes us talking about how we generated our signals for testing experimentation. We'll now go on to how do we, we'll go on to the results, right? So here we have our 2 plots. On the left-hand side here, we have our transmit and receive signal, which was being shown in real time at that point. And on the right-hand side, we have the range Doppler map that was produced. So we have, our target was kept in the center during experiment and testing, just to make it easier to see. And then you can see our 2 pieces of stationary clutter appearing around, specifically above and below it. So what this shows is that we were successfully able to take these recordings, offload that cross ambiguity function off to the FPGA board for processing, send that data back to GNU radio, and then visualize the data. So now we're going to measure the performance, right? We want to know how well does this actually perform. So we use 3 different types of hardware. First, we use our developer laptop. This served as a benchmark for our FPGA implementations. So instead of offloading the cross ambiguity function to an FPGA, we instead performed it locally on the laptop using Python, and you can see the specs for the laptop below. Additionally, we use the pink C2 board in the middle here, the pink board, which is more of a hobbyist board. Usually you can get one for about $200 or less. However, still a very capable and good board for what it is. And finally, we'll be using the CCU 102 board, considered a more high-end FPGA board, which has a better onboard processing system and more FPGA resources, which we actually made use of. So there's a difference in the implementations between the 2 boards, where the pink board used mostly LUTs for its FFT within its cross ambiguity implementation, while the CCU 102 used mostly DSP resources in its FFT within its cross ambiguity implementation. So here on the next slide, we'll look at how they actually performed. So, my bad, I forgot, we actually added flow graphs first. So this is how we tested the FPGA boards. Same flow graph as earlier. We are reading from the text files from the left. We are passing them to our client, which is offloading the computation to the FPGA board. It's returning that output and then displaying the results in the matrix sync. We timed performance in this graph in 2 places. So we timed it within the cross ambiguity client within GNU radio. This was to measure the latency that occurred due to having to offload and send the data off the laptop to an FPGA board and then receive it back. And then we also timed the computation on the FPGA board itself to see how long it took to perform the cross ambiguity function. For our developer laptop, we used the same flow graph. We just disabled the cross ambiguity client since we weren't offloading the cross ambiguity. And instead, we implemented another embedded Python block here, the cross ambiguity function -Python. And this just had our Python implementation of cross ambiguity and formed it locally on the laptop. And we timed the performance within that block for the laptop. So now is the results. So we'll break this down. So blue is the developer laptop. That reddish orange color is the pink C2 board, the hobbyist board. and the yellow is the CCU102, the more high-end FPGA board. The y-axis here is the time it took to process in milliseconds, and the x-axis is the number of bins increasing from left to right. You can think of the bins as being the size of the output matrix of cross-ambiguity, where the higher number of bins means a higher resolution you have in your final range Doppler map. So something that can be noticed here is that the FPGAs performed better overall than the developer laptop. Something that did stand out to us was that the last two bins, the 128, 128, and 256 by 256, we see that the red bar, the hobbyist bar, actually performed slightly better than the CCU102, the high-end board. Why that is, we haven't really looked into too much, so we don't really know at the moment. It could just be, a matter of a little bit of error, it could be considered, negligible. It's only about 2 milliseconds of difference. But yeah, it's up to, further investigation, right? So then we'll look at the latency times recorded. So here, the colors are the same, where red is our hobbyist board, yellow is our more high-end FPGA board, y-axis is the time it took to process in milliseconds, and x-axis, again, is the bins increasing from left to right. So overall, we see that the high-end board handled the latency better overall than our Pink Z2 hobbyist board, most likely due to its more capable onboard processing system. Additionally, though, latency is a major factor in the setup. So if we look at the previous slide, let's look at the very last bin, 256 by 256. The Pink Z2 board processed cross-ambiguity at 6 milliseconds, and then the CCU102 at about 8 milliseconds. So 6 and 8 compared to, on this slide, 30 milliseconds and about 18 milliseconds. So the latency for the hobbyist board is about 5 times as long as the cross-ambiguity computation, and for the more expensive board is about twice as much. So certainly a factor in the setup. So conclusions. This work did help to develop a basic hardware-in-the-loop simulation for testing radar and validating radar algorithms, specifically the cross-ambiguity function using Pink and the GNU radio. We also conclude that the FPGA boards, or at least the implementations on the boards, performed better than the development laptop when it came to computing cross-ambiguity. However, latency was still a major factor in this setup. Future extensions of this work could look like implementing lower latency data transfer methods. For example, the CCU102 board has an onboard PCI port, or you can also make use of the onboard SFP ports as well. You could also potentially ditch the data transfer totally from the laptop to the FPGA board and potentially run everything on the processing system of the FPGA board, which may be more ideal. Another extension could look like offloading more of the digital signal processing chain to the FPGA fabric. So filters such as a fur filter or a clutter filter would be really nice. And finally, investigating performance with higher number of bins. So we only went up to 256 by 256 due to resource limitations on the hobbyist Pink Z2 board. It would be interesting to see a implementation that used less resources and was able to go higher on that board, or if the CCU102, the high-end board, was pushed to more higher bins. So with that being said, that concludes this presentation. Thank you everyone for joining in. Thank you for anyone online who joined in, and that concludes this. Are there any questions? We have time for questions?
Yep, we have time for a couple questions. Anything from the audience?
Well, thank you.
All right.
All right.
Oh, hold on. One question.
Yeah, I need to hear it again too.
Do you do any formal verification between the Python code you used to develop the application and the FPGA code, if you will, that you end up with?
Could you elaborate a bit more? Just like, what do you mean?
Well,
I don't understand.
To prove that the two programs are semantically identical, that you get the same answers out regardless of the implementation.
Okay, do you mean like comparing the two numerically against each other?
Well, that's one aspect, yes, yeah, one aspect.
Yeah, well, when we compared the matrix from the FPGA output to the Python output, we saw that there was like a 0.00003 difference on average between the two. So really, most of the verification was done visually. There was some done in the math, but we usually found the error to be so low, we didn't consider it. Yeah. I'm sorry, does that answer the question? Okay, thank you.
All right, any other questions? All right, let's give a round of applause for our speaker. Thank you very much.
Thank you.
And next speaker, please make your way to the stage. All right, next up we have Jose, who will be talking about GR-PhysSec, real-time channel-based key generation for physical layer secure wireless communications.
Is it here already? I'm finding it. I think it's this one. Nope, it's not it.
So it should be here.
Around
Right there. PhysSec, right? That one?
this one. All right.
That's yours.
Yeah.
Go ahead now.
Awesome.
I guess presentation mode.
Good. Awesome. All right. Hello, everybody. I am Jose Sanchez. I will be presenting to you GR-PhysSec real-time channel-based key generation for physical layer secure wireless communications. Then this is, oh, you're not hearing me? Better? There you go. This is a working collaboration with Dr. Georgios Klyonitis and Dr. Dimitris Sparos at the Center of Connected Autonomy and Artificial Intelligence at Florida Atlantic University. And well, first, what is physical layer security? Let's say we have Alice and Bob, two nodes that would like to exchange or establish some communication. And due to the fact that RF communications are open in the air, then any eavesdropper or any other node that is able to listen to the same center of frequency is able to also listen to whatever we are exchanging on that channel. Now, the point is that we would like to ensure that there is no leakage of information to these other nodes that may be passively or actively listening for any other reason. Now, one way of securing this is through, let's say, symmetric key encryption, right? This would entail that we go generate some keys back at some central station, and then we distribute these keys in, but we would need a secure channel in order for us to do that. In the other end, we could use public key encryption. This would entail that the public key cryptography is usually very highly computationally expensive. Now, we could do it another way, harnessing the physical layer through harnessing the features from the channel, which is at times, if we do it fast enough, it's reciprocal. And how can we do this? It's usually a 5-step process. We go first, Alice and Bob exchange some probes, right? Then, based on based on the impulse response, we extract some features using any method that we could perhaps do. Then, let's say feature estimation or something like that. Then, based on these features that we extract out of the channel, we go and create a key, right? Let's say, quantize the features and produce a binary vector. Based on these binary vectors, due to the maybe changes, temporal variations of the channel, this is probably not going to be perfect. So we need to reconcile this information between Alice and Bob. And finally, after reconciliation, we will end up with a similar key that we can amplify the privacy through, let's say, some hashing algorithm. And what is the impact? The impact would be on-the-fly key sharing, right? So we would be able to, on-the-fly, generate keys whenever we want without the need of a centralized server. And any node that joins the network could also generate these keys on the fly. yeah, and yep, I covered all the points. All right, so our proposed key generation method uses a neural network for channel feature extraction. So we went ahead, we gathered a bunch of training devices, we gather our training data set, and then we develop a neural network channel feature extractor for extracting features out of the channel, out of the probes that are exchanged by Alice and Bob. So to the right, yes, you have our proposed method would go Alice and Bob exchanges some probes, then they go ahead and apply short-time Fourier transform for, and then using this transformation, we go and feed this into our neural network, extract some features. Using those features, we go ahead and quantize them. Then, based on these quantized features, we go and Alice or either Alice or Bob, they go ahead and send the parity bits to either or. Then whomever receives that then tries to reconcile, and then use some sort of private amplification method such as SHA 256 or 128 or 512 to amplify the privacy of the key. Now for this, we have developed a few blocks to do this through New Radio. That would consist of our pre-processing methods, which is just the STFT and the neural network extractor. So we develop a block for both of those steps. And then also blocks for the quantization, the parity bit generation, and reconciliation, as well as the privacy amplification methods. There you go. So our channel feature extractor, after Alice and Bob exchange some probes, then we go ahead and pre-process these IQ samples using STFT and log power scaling to produce the neural network input, which would be our spectrogram. And then on the feature extraction block is just a block that accepts a file. This would be our neural network in ONNX format that has been imported into ONNX format. And then we use ONNX runtime for performing the inference. Then under the neural network input, we just have the spectrogram, goes through all of our layers, and then we produce an output, which in our case, it's a 512 sigmoid dense layer, which would be our feature vector. Then using, I think that's good. Then using our feature vector, we proceed to quantize these features using, we just use mean thresholding for quantizing the feature vector. So any value that would go over the mean, and we set it to a 1, and otherwise we set it to a 0, and we produce our binary feature vector. These are some of our results that we tested at the lab. Oh, I think I missed one thing over here and below. At the lab, we set up our test bed to have two robots and then we mounted on top of them a Pluto SDR and together with Jetson Orion. And then we went through the whole protocol that we see there. And then on the results, we went ahead and started exchanging probes. Then on those probes, we went ahead and generated our feature vectors. And then on the feature vector, we quantized them for 100 times. And while the robot was stationary, we obtained bit disagreement ratios around 0.3 and 0.03. That's 3% or 10%. While moving it, so there's actually an issue introduced by the factor that the robot is moving, and then this introduces more errors into our quantization method. So we just get higher BDRs while the robot is moving. So these are just some things that we could improve upon after this conference. And then, of course, after we have, due to the fact that there are bit disagreement ratios higher than 0, then these keys are not perfect. So we need to reconcile. Yep. So we need to reconcile these two private keys that have been generated by Alice and Bob. We use Reed-Solomon encoding for Alice to produce the parity bits. And then Bob uses the same Reed-Solomon decoder to reconcile the differences with the parity bits that Alice has sent. Yeah. And then we have developed 2 blocks for this. So either the node that will be generating the parity bits will use the parity generation block, and then on the other hand, the node that will be performing the reconciliation will use the reconciliation block. And those are some of the results on the reconciliation side, where we can see that it goes very well in that threshold in between 3% and 10% bit disagreement ratio, but after we start moving and we introduce more errors, then it just drops. And then private simplification. To enhance the randomness of the generated key, we use SSH3 hashing family of hashing algorithms. Our block supports multiple hashing algorithms that you can use. So you can either use 128, 256, or 512. Maybe in the future we can support other hashing algorithms and introduce them, so you can use any method that you prefer for hashing your key or introducing more privacy. And then we tested the generated keys or the successfully generated keys using the NIST statistical test suite to ensure that, or to test whether our keys are actually random, right? And we're actually generating random keys. And we did pretty well. And then, well, this would be the flow graphs. So, so this would be Alice's flow graph. It starts with, in the middle, Alice's controller. We had to implement some control flow in order for us to do the full implementation of the Alice and Bob exchange. Right now, it's not an RF communication. We are just using CMQ publisher and subscriber message blocks, and then these are just communicating over IP. But once Bob, either Alice or Bob starts, in this case, Alice is the one reconciling, so Bob starts, sends Alice a message that says, hey, can we start exchanging probes? Then Alice is gonna accept. Alice is gonna get or open her RX gate. This RX gate is just another block that we created so that we wouldn't be streaming constantly received signal or noise through the whole all of the blocks, but only when Bob was actually sending the probe. So that's just the RX gate. Then once that goes through, we get 8,125 samples. We feed them into the spectrogram block. Then we feed that into the feature extraction, then the quantization, and then Alice will generate the parity bits. Now, using the generated parity bits will be sent to Bob through another publisher, CMQ's publisher message sync block. But then Alice will go ahead and just amplify her key and wait for Bob's response to whether he was successful for reconciling. And then on Bob's side, he will do the same. He will wait for Alice to say, hey, I have accepted that we are going to be exchanging some probes, so this is my probe. Bob is going to open the RX gate, it's going to get the samples, it's going to go pass them through all of the blocks, the spectrogram, the feature extraction, the quantization, and then upon receiving the parity bits, then it will go ahead and reconcile, and then after reconciling, I actually have another monitor that tells Alice whether it has been successful or not. And, but upon success, then it will feed that into the private simplification block and then save the key. And this is a video of the implementation that hopefully runs. There you go. So that's me, and on the bottom, that's some of the robots that we have at the lab. And then I'm just running GNU Radio Companion on each of the robots in there, or my nodes. Those are just the flow graphs. Just, can I pause? Yeah, there you go. Some of the differences, of course, this has many more blocks, but some of the key differences that you can see there is that I just have a monitor block, some monitor blocks that are just extracting information for a monitor that I have created that monitors the whole thing happening in real time, which is going to, but that's just the only difference from what I have, from what you have seen before, besides also the message debugging, just for debugging purposes. And yeah, that's just running. And I guess, yeah, so there we are going to be able to see kind of like everything loading, the model being loaded, and then so that we can actively extract features. And then that is just the monitor running, and then so we can follow every step of the process. And this is happening pretty quick, even though not as fast as we plan to, but it takes around, we are measuring the time, the key generation time, the success rate, and the bit disagreement rate. Right now, the robot is stationary, so there are no many errors during the bit disagreement, but in a moment while we move the robot, we're going to see more perturbances, and then we're going to start seeing that the success rate is not as good, even though it's not so bad, right? It's but yeah. There are also, oh, but by the way, what our probe is just a it's just a tone, right? So that's really all we're sending over there. Yeah. And yeah, which is one interesting thing that you can see in between the bit disagreement ratio and the success rate is whenever we have high bit disagreement ratios, the success rate will just fail. So it's just a good metric to have to see real time. And also the effects of the visualization of the spectrograms. Whenever we see something, that it's too different in between both the spectrograms, it's just, yeah, we can see that we probably fail. So, and yeah, there you go. And that's it. So the data, it's all available, and the code, it's also available all on that repository. And the demo is there, and then, well, we have to acknowledge our sponsors, the FRL and the NSF. Thank you very much for your attention.
All right, thank you very much. I know we're running a little bit late, but we have time, maybe one question? All right, hold on.
Thank you. Maybe I missed that, but why is it a good idea to have a neural network for the key derivation method?
Yeah, one, it's not that it's necessary. per se, but it's just another method for extracting features out of the channel. And the reason why, or we haven't made a formal comparison of every method with our method, but our method is looking into ensuring or training the neural network such that we the features that are extracted through Alice and Bob, which should have a very good spatial, we should have a similar channel features, are very far apart from the spatial variation that would have a third node, let's say if. So during our training process, actually here, you see that we actually collected samples from Alice, Bob, and a third node, Eve. And then through this, our training process, we try to actually enforce that this principle, right? To enforce that the features that are extracted by Alice and Bob are very close together, enforcing the channel reciprocity principle, but maximizing the spatial decorrelation that these two nodes would have with Eve. So that's just our thought.
Okay, thank you. And how do you make sure that the neural network is not outputting 10 different types of keys? Or, I mean...
10 different types of keys? Or
yeah, I mean...
I'm so sorry.
Yeah.
I recommend this
No,
conversation
we can catch up
absolutely
later.
continue. It's lunchtime, but before we break, I had a couple announcements. But real quick, let's give another round of applause. And please, I know there are other questions.
go back to the first slide. Let's see, there we go. Okay, cool. Can you guys hear me okay? So my name is Gavin Messerly. I am currently a graduate student at Weber State University working on my master's degree in computer engineering. And I'm also an electronics engineer for the 309th Software Engineering Group with the Air Force at Hill Air Force Base in Utah. And the project that I'll be introducing and presenting on today is my capstone project for my degree. And this project was actually the first official engineering collaboration between Hill Air Force Base and Weber State University, looking into research on developing software-defined ground-penetrating radar using commercial software-defined radios. So just a bit of overview about this project. So the 309th Software Engineering Group is wanting to do research into different avenues for landmine detection, specifically ground-penetrating radar. So the goal of this project was to evaluate whether or not a software-defined radio could viably replace a traditional GPR system for detecting shallowly buried targets, and then comparing those results with an industry standard and commercial ground-penetrating radar. So just some background on ground-penetrating radar. As the name implies, GPR is a radar that is designed to identify objects in the ground. So the left image here shows the working principle of a GPR. So GPRs are generally bistatic systems with the transmitting antenna transmitting some signal and then the receiving antenna receiving some reflection off of a submerged target and using that signal to determine where that target is. The middle figure here might show an output of what a GPR system would look like. So shown here is what's called a B scan, and each individual line on this B scan is called an A scan. Where an A scan is basically a one-dimensional ping just saying how far away is this target from me. And that two-way time delay of where that reflection shows up correlates to how far away that object is. So you can kind of imagine those two antennas on the left sweeping over some submerged target. You would create this kind of hyperbolic shape. And this hyperbolic shape that shows up on B scans shows that there is a target present there. And the peak of this hyperbola is where the target is actually located. Now, traditional GPR systems are generally done either in a handheld device or a pushcart device, as shown here, where you have someone physically surveying an area and moving, pushing the antennas to actually survey the specific area you're looking for. But recently there's been a lot of interest in drone-based GPR systems. They've been shown to reduce labor, to reduce time, and especially in landmine detection to reduce risk for the user. The problem with this is that traditional GPR units are expensive, they use a lot of power, and they're really heavy, which is not ideal for a drone payload, meaning you either need a very large and expensive drone to be able to carry your GPR, or you get little to no flight time on a smaller and cheaper drone. So software-defined radios are a potential solution to this because they're cheap, they don't use a lot of power, and they're very small and lightweight, which is very suitable for drone applications. So the approach that was taken to test whether SDRs are viable GPRs goes as follows. So the type of radar selected to implement on the SDR was a stepped frequency continuous wave radar, or an SFCW radar. The reason it was chosen is because these types of radars are capable of getting very high signal-to-noise ratios and not needing a lot of power to do so, which is ideal when you're working on an SDR platform. The SDR used was a Blade RF 2.0 from GNU, and then all of the software for this project was written in GNU Radio Companion for the real-time signal processing and hardware interface, and then additional processing was done in Python as well. Now, step frequency continuous wave radar operates a little bit differently than a traditional radar system. So in a traditional time-based radar or impulse radar, you transmit a singular impulse, and then you wait for some reflection, wait for a certain amount of time for some reflection off of a submerged target. And that two-way time delay is what you're measuring that correlates to the range or how far away that target is. Conversely, an SFCW radar actually, instead of transmitting an individual pulse and measuring the time delay, will transmit a continuous set of frequencies and then measure a phase shift between the received signal and the transmitted signal. Now, pictured on the right is probably the simplest architecture you would need to implement this type of radio or radar. And it all starts with some frequency synthesizer that's generating n discrete frequencies over some band, one at a time. So you transmit your first frequency for a set amount of time, and you keep stepping up until you get across your entire band. And that's visualized there on the left with a frequency domain and a time domain waveform showing an SFCW signal. On the receiving end of things, you are more or less collecting magnitude and phase information for n discrete frequencies separated by some delta f over a band. Now, by definition, this correlates to the discrete Fourier transform of some time domain signal. So what you can do is with that data, you can synthetically create an impulse time domain waveform by taking the inverse Fourier transform of all of that data that you've collected. And that synthetic time domain would actually look as if you were operating on a traditional time-based or impulse waveform with the reflection off of some target showing up at the timestamp that would correlate to its two-way time delay. So in this way, this type of radar actually operates in the frequency domain and then synthetically creates the time domain after that. So these two equations on the left are the dictating parameters for how SFCW work. The first being delta R, or the range resolution, which is how close two objects can be to each other before you can no longer distinguish them as two separate objects. And then R max is the maximum unambiguous range, or the maximum range that your radar can detect an object before you start to see false targets from aliasing. So by choosing our bandwidth to be 2.5 gigahertz, ranging from 600 megahertz to 3.1 gigahertz, with 100 discrete frequencies separated by 25 megahertz, in theory, this radar would be able to have a range resolution of 6 centimeters and a maximum range of 6 meters. Now, before we wanted to physically implement this and put it to the test in a lab, we wanted to simulate it to prove that the radar parameters that we selected, as well as the signal processing that was implemented, would be able to work in the environment that we are operating in. So pictured here is the architecture that was simulated in Python. And now, like I mentioned, the radio that we were using is the Blade RF, which traditionally is a direct conversion receiver. However, direct conversion receivers have a big problem with large DC offsets. So to avoid the large DC offsets that are traditional with this type of receiver, we actually operate the Blade RF as a low intermediate frequency receiver, or a low IF receiver, with the biggest difference being that the transmitter oscillator and the receiving oscillator are offset from each other. So you're down converting to an offset frequency before sampling, and then you do an additional digital down conversion afterwards so that you can filter out to that DC offset. Now, a benefit of step frequency radar is that you get to choose how long you transmit each frequency for. Thus, you can average your signal for as long as convenient for you to increase your signal-to-noise ratio. As such, we have a block that averages all the samples collected for each frequency to improve our SNR, and then the inverse Fourier transform is taken to show that time domain waveform. Now, actually simulating a reflection in Python comes from making the approximation that a ground-penetrating radar system is linear in time invariant. Now, if we make this assumption, that means if we were to get some impulse function representing our system, we could convolve any valid radar waveform with this impulse function to accurately simulate a reflection off of a target in our system. So to be able to create this impulse function, we used an open source electromagnetic simulation software called GPR Max. In GPR Max, a visualization of this software can be shown in the top left corner of that figure. So GPR Max lets you set environment parameters such as the size of your environment, the medium you're propagating through, the type of object you're trying to detect, etc. But the most important thing you can set is the type of waveform that is used to actually propagate through the medium. So pictured in the top right corner and the bottom left corner are corresponding A scan and B scans from running this simulation using a traditional radar waveform, a Gaussian dot norm pulse. So you can see the big pulse at the beginning representing the direct coupling between the antennas, which is the transmission path directly from the transmitter to the receiver, and then the smaller pulse afterwards, which is the reflection off of that target. Now, if we rerun the simulation, but changing the waveform from a Gaussian dot norm to an impulse response, or an impulse function, you get the picture in the bottom right corner, which is the system's impulse response, which is pretty meaningless as it is. But by convolving our stepped frequency waveform with this impulse function, we can simulate each frequency that we're transmitting reflecting off of that target. So the Python simulation does just that, generates the frequencies, performs the convolutions, and then does the inverse Fourier transform to create the results here. So if you were to compare these results with the A scan and B scan on the previous slide, you'll notice we'll be able to verify that the simulation does work and that the parameters that we selected are going to work well for our environment. One other thing to note from this simulation is you'll notice as the target gets closer and closer to the antennas that the reflection from that target will continually get lost in the direct coupling of the antennas, and you won't be able to see the target anymore. So it's very important when detecting shallowly buried objects in GPR that you remove that direct coupling or reduce it as much as possible. And I'll talk a little bit more about that later. So after the simulation was able to prove that it was working, we could go move to hardware implementation. So like I mentioned, the radio we're using is the Blade RF, which is a 2x2 transceiver, meaning it's got 2 transmitters and 2 receivers with a wide tuning range from 50 megahertz to 6 gigahertz. The antennas selected for this were TSA 600 Vivaldi antennas from RF Space. Vivaldi antennas have been shown to have high performance over wide bands, making them very good for GPR applications. And then you'll notice with the picture of our rig on the right side that we do have a metal plate, metal shielding between the antennas to further isolate them to further reduce that direct coupling. Now, one issue that we had with this Blade RF is that because the Blade RF is meant for high-speed data applications on multiple frequency channels, the transmitter and receiver do have separate oscillators. It's been shown that these oscillators do produce the exact same frequency but have a non-deterministic phase difference between them, which makes it nearly impossible to actually measure phase with this radio alone, which is kind of important when you're dealing with a radar that needs to measure phase, right? So in order to actually measure phase using this radio, we had to make use of the second transceiver on the Blade RF. So pictured here is the entire system architecture. And on the right side, you'll see the analog signal chain. Now, this is the analog signal chain for the Blade RF. So you'll notice the 2 transmitters, the 2 receivers, and then again, note the 2 different oscillators between them. And then on the left side, we have our digital processing, with the middle section being done in GNU Radio Companion, and then the post-processing block that was done in post after a measurement was taken. So GNU Radio Companion generates a constant signal, and this is modulated up with the oscillator. And by varying the oscillator carrier frequency, that's how we create the stepped waveform. This is transmitted over the first transmitter and then received on the second receiver. And then it follows the normal low IF signal chain after that. But you'll notice that the second transceiver is used by directly coupling TX2 to RX1. Now this is done and is used as a reference line so that we can measure the exact signal that we're transmitting. And further down the receiving chain, you'll notice that we divide our received signal by this reference line. By doing this, we're able to actually divide out any phase difference between the transmitting oscillator and the received oscillator dynamically for every single sample that we take. Which means the only samples that are being averaged are magnitude and phase information for frequencies that are being caused purely by a reflection off of a target and not by the oscillators. And then, like I mentioned before, direct coupling is a problem. So also in post, we implemented an additional static clutter removal algorithm to remove the coupling from the scans so that the targets can be more clearly seen. So this is a quick block diagram of our software. So a main controller that was written in Python starts this system by the user entering the radar parameters, the scan parameters, and that's used to initialize a subprocess for the GNU radio module. Like I mentioned, the GNU radio module handles the hardware-software interface as well as the transmitting and receiving, and will save all of the data it collects to a known storage location. And then when the GNU radio companion module has hit the end of its scan, it will close and the main controller will take over again, grabbing all of that data that was collected and performing all of the post-processing scripts after that. Now, it's been shown that the transmitter and receiver have varying frequency responses as the frequency increases. Thus, to actually get any meaningful results out of this radar, both the transmitter and receiver need to be properly calibrated. To properly calibrate the receiver, 2 phase offsets need to be handled. The first one was what I mentioned earlier, which is that phase difference in the local oscillator. The second phase offset is actually introduced by the signal chain itself, or the signal propagating through the hardware and then back again. So while the local oscillator phase difference is non-deterministic and has to be handled dynamically, the signal propagation offset is constant and can be measured and can be fixed by just applying a singular phase shift to your data on all subsequent scans. So it was measured by putting a metal reflector 1 meter away from the radar in open free space, and then the two-way time delay was measured for that. And that was correlated against what the two-way time delay for a metal reflector at 1 meter should be, and then a phase shift was applied to the received data to match that up. And that phase shift, that phase offset was saved as a constant, so all subsequent scans are just shifted over by that same amount every single time, so that all of the time delays can properly show the accurate results. For the transmitter, the transmit power varies as the frequency varies. Thus, to increase your dynamic range of your receiver, your transmitter gain should also vary. It's also important to note that the shielding that is placed between the antennas is more effective at attenuating higher frequencies than it is at lower frequencies. So if the goal is to reduce your direct coupling as much as possible while also increasing your signal to noise ratio as much as possible, a hypothesis was tested where if we linearly ramp our gain as we increase frequency, we give higher power to the higher frequencies that the shielding is good at attenuating, and lower power to the lower frequencies that the shielding is not as effective at attenuating. So this was tested by putting a soda can 1 meter away from the radar, a smaller target, and then some A scans were taken. So the bottom row shows 3 different A scans, with the big pulse again being that direct coupling, and then the smaller spike about 1 meter away, indicated by the arrows, being the soda can. And if you take a look at the top row, that is the relative power between the direct coupling and then the soda can. And you can see by that power plot that we get about a 3 to 4 dB of improvement by linearly ramping the gain, meaning that our direct coupling has decreased while the rest of our signal has increased. And it can even be visually seen on the A scans that the soda can is much more apparent against the direct coupling and the rest of noise by linearly ramping the gain. So once the radar was designed and everything was properly calibrated, we could begin physical experimentation. So pictured on the right is our experimental setup with our test bed created by embedding 2 different targets within a foam as our medium. The 2 targets selected, and one of them is shown here as a pt2, and the second one was a soda can. And then you'll notice our radar is mounted to a 3D printed test rig that's attached to a camera slider. And a camera slider was used so we can get controlled, repeatable movement across the test environment for subsequent testing. And then shown in the top left corner is the commercial GPR that we actually compared our results to. So by sweeping both of these radars across the test environment, these were the results we were able to get, this one specifically being the soda can. So both targets, the soda can and the pt2, were buried 15 centimeters deep, about 50 centimeters lateral, so like roughly the center of our test environment. And you can look at these results and see that the commercial GPR and the SD GPR are doing a comparable job at actually identifying the target that's embedded in the material, and this is the results with the pt2. Now, one big difference that you'll notice between the commercial GPR and the SD GPR is how much better the horizontal resolution is for the commercial GPR versus the implemented SD GPR. And that drastic difference in horizontal resolution comes from probably the most difficult challenge faced in this project, which is how long this radio takes to tune from one frequency to another. Now, according to the Blade RF documentation, it should take roughly 400 microseconds to tune from one frequency to the other. However, we were getting something drastically different than that when we actually tested it. So we did a quick echo program by connecting the transmitter directly to the receiver and swept through our frequencies, saved that data, and displayed it onto a software that could look at spectrograms. So the green lines represent the time that we are actually receiving data. The blank space between the green line is the time that our radio is retuning, and both of those times added together represent our transmit time, or tau, as shown here. And you can see for these 2 different transmit times that our retune time that we are getting is roughly 10 to 15 milliseconds, which is drastically different than what the radio is supposed to be able to do. On top of this problem, we noticed an additional delay when tuning from below 1.35 gigahertz to a frequency above 1.35 gigahertz. Every time you would try to go across this boundary, does not matter what the step size was, the time that you spent receiving the data was drastically delayed up until about 110 milliseconds. So that the process for retuning to the next frequency would be delayed, which is shown by T delay here. Now, this isn't really a problem for the top two plots with the longer transmit times of 175 milliseconds, but this becomes a problem on the bottom two plots on the shorter transmit times when your delay is actually longer than the time that you're transmitting each frequency for. This means that we are skipping frequencies because the software is trying to move to the next frequency before the hardware has actually finished retuning, which ruins your radar results if you skip this many frequencies. So in order to actually avoid these two problems without having to rewrite the entirety of the software was to set our transmit time to 100 milliseconds, which for 100 frequencies gives us a PRI, or pulse repetition interval, of 10 seconds to generate one A scan, which is painfully slow. Even operating the camera slider at the slowest possible speed it can go, we are only able to get 20 A scans across that environment, whereas the commercial GPR is more likely getting hundreds to thousands of scans. But despite the longer transmit time and the poorer horizontal resolution, the proposed SD-GPR does deliver a comparable performance in identifying submerged targets for shallowly buried targets, showing that SDR does show promise as an alternative for ground-penetrating radar if that retune time can be adjusted and fixed. So shown here are the actual measurements that were received, and the far right column is the average error between the two, showing the comparable results between them. So future work for this project is going to be addressing the retune time to be able to actually get a feasible PRI out of our system. And other future work includes a more defined static clutter removal algorithm, switching to a real-time display so the user can see the B-scan as it's being constructed, and then switching to a wireless interface in preparation for a drone implementation. But that is this project in its entirety. Do you guys have any questions for me?
Thank you, Gavin. Any questions?
Chuck?
So when you were switching frequencies, how far apart are they, and how far apart are they?
They're separated by 25 megahertz.
25 megahertz, okay.
Yeah, so with a band of 2.5 gigahertz, that gives us 100 frequencies across the entire band.
All right, thank you.
Did you collect and analyze the COTS ground-penetrating radar waveform to see what they were using?
No, we did not have time to actually characterize the type of radar or waveform they were using. I know that specific radar is meant for concrete scanning, so I know that the band of frequencies they're using are the same band of frequencies that we are using, but shockingly, they don't have any documentation that says what kind of waveform they're using, and no, we didn't characterize the type of waveform at the time.
I have a question. Did you pick the foam and the type for a specific reason versus rebar and dirt, or?
So the foam was chosen because it's low loss, which is ideal for these initial GPR testing that we were doing, especially because we didn't, like this entire system, you can see is actually powered off of a USB cable on my laptop. So I didn't have an external battery to really push the amount of power to do a full test penetrating through the ground. But that future work past getting the radar to speed up in its acquisition would be to separate it from that USB cable, making it wireless, in which case it would be powered by a battery and could pull more power from it. So.
One more question. Sorry, other question?
Thanks. So considering that the actual stepping in frequency seems to be like time constrained here, have you considered other waveforms than the usual step frequency, CW or chirp, steps chirp, things where you observe one frequency for longer, get a better SNR for that frequency, and then interpolate with fewer steps, with more spectral gaps between that?
I'm sorry, do you want to elaborate a bit more?
So your current waveform is step frequency radar, right? So you stay constant for some time on one frequency, then you tune to another one, do that again.
Yeah.
But you could also use your bandwidth at one point and get like a higher resolution for one sampling bandwidth and repeat that and interpolate. That's kind of a trade-off because you're kind of trading SNR for range resolution. But it could save you a couple tunes. So is that a direction you might take now that you've got the design freedom of an SDR?
So the initial thought process right now for why it's taking so long to switch between the frequencies is the fact that it's written in Python. And because it's written in Python, the documentation claims that the read tune time is for the C API, and then there's a Python wrapper over that, and then GNU Radio Companion has its wrapper on top of that. So if the project was redone in C++, which GNU Radio Companion can compile in C++, but half of the blocks we're using would just have to be rewritten. But doing that, I think we could drastically increase the speed. So right now, that's the current plan, is that continue to use the same waveform, but try redoing it in C++ and see if we can get that tuning time increased.
That's interesting. I was thinking that was like a hardware, like the actual tuning time of the tuner was the critical thing and not the time, like say, send a command, wait for it to tune, and then get the result back. Okay, thanks.
All right, that's probably good. We'll give it up one more time for Gavin. Thank you.
Thank you.
And next up, we have Cody, who's giving a talk on GNU radio-based tool for synchronization of SDR radios, SDR in a distributed radar network. Thank you, Cody.
How do I get this up here?
That switch over. Coming up.
Is it up yet? Question mark?
There you go.
Gotcha.
Yep.
Cool. Awesome. Hello, everyone. My name is Cody Q. I am a master's student at the University of Oklahoma, where I've been working at the Advanced Radar Research Center under Dr. Russell Kenny and Dr. Justin Metcalf. And today I'll be talking about my outer tree module called GR Harmonia, which focuses on synchronizing software-defined radios in a distributed radar network. So with this slide, it's just a brief outline of what I'll be talking about today, and we'll go straight into the introduction. So with many radars today, they are traditionally monostatic radars, which means that there's one platform transmitting and receiving to detect targets. But with using distributed radar systems, they have multiple nodes that transmit and receive and can help improve detection and imaging in comparison to monostatic radars. And another benefit that they have is that there's no single point of failure as well. So one of the main key issues with distributed radar systems is that you have to synchronize all the nodes. And for that, there are three main components, which will be clock drift, clock bias, and carrier phase, which correspond to frequency, time, and phase. So if I can divert your attention to the top right plots, on the top row, we have SDR1 with a specific set of frequency, time, and phase values. And then SDR2 has a different offset in comparison to SDR1. And if we were to sum that up, you could see that there is a huge loss of data whenever we add up SDR1 and 2's waveforms. And so we will first define clock drift, which is the true frequency of the clock divided by the nominal frequency. And then clock bias will be the time offset, where we could define the local time of platform I to be the clock drift times the true time plus the clock bias. And then there will be carrier phase, which will be from the independent and random offsets from the up and down conversions from the local oscillator. And so from there, the bottom equation shows from a transmission of platform J to platform I, the mathematical derivation of how these three will affect the signal. And so next, we will discuss more upon the actual synchronization algorithm used. So an important thing to note for this algorithm is that it enables synchronization fully digitally in the digital domain. And there are 3 assumptions that are made for this algorithm. The first one being that for platform I, the independent main oscillator has a nominal frequency and a true frequency, as stated before. And then for this project, each platform will be stationary. And then the last assumption that we have is that there is coarse synchronization done beforehand, which should allow the clocks to be aligned within a few milliseconds from one another for each platform. And so how all the SDRs will be communicating is through the time division multiple access scheme, which allots specific time slots for each platform to transmit their own signals. So for a platform, system of 3 platforms, it will have user 1 transmit, wait, then user 2 transmit, wait, and then have user 3 transmit. So for the first estimation that we will have is clock drift and offsets on the transmit and receive. And then to go further into that, so once a singleton waveform is processed and converted into the frequency domain with an FFT, it uses sync nonlinear least squares to interpolate it further to further improve the estimation of the frequency. And then with all that, they exchange the values again and use the following equations to estimate for clock drift, assuming that SDR1's clock drift is set to 1 or unity. And from there, we'll have the clock drift values. Here is how it is adjusted for the transmit and receive. It does a time dilation with the estimates and also a carrier correction. And that will allow for frequency synchronization. The next step is clock bias and carrier phase estimation, which uses an LFM instead and has the same algorithm where it will broadcast and then each SDR will start to receive and estimate for time delay and phase. And then the platforms will then share their time delay and phase estimates with one another to solve for things like range, clock biases, and carrier phases. And with that, they can start compensating for their errors in the transmit and receive as well. So going into depth about this estimation, it does a match filter with its transmitted signal and the received signals to produce a sync waveform, which then we could start using the sync nonlinear least squares to further improve the time estimates, which was given by the variable m. And from there, all the SDRs can start to share this value, their estimated values of m, with one another to then be exploited with the symmetry to compute range and clock their biases differences. And then further computing on, we can then compute for their network average of clock biases and then estimate of carrier phases, which can then, with the carrier phase differences, we can use linear least squares to calculate the carrier offsets for the transmit and receive. And then lastly, we then compensate with some fractional delays of the clock bias for the transmit and receive, and then also a phase correction for the clock bias, and as well as the carrier phase. And once that's done, the whole system should be able to synchronize all their waveforms together. So with that, we have the module that I created, GR Harmonia. I split it up into 5 different sections, being waveform generation, UHC controls, clock drift estimation, clock bias, and carrier phase estimation, and then waveform compensation. So for the testing and purposes of this block and the algorithm itself, I decided to implement all SDRs on one single computer. So that will affect how a lot of the blocks are implemented. And with that, all blocks will operate in the message domain where they exchange protocol data units, or PDUs. And here on the block, or in the block diagram below, is how I will set up all the blocks together for the flow graphs. And so first we have waveform generation. We have a single tone block which generates the data and exports it as a PDU with a label saying that this is a single tone as metadata. And then we have the LFM source block, which takes in the estimates, clock drift, carrier bias, or clock bias, carrier phase, and it then adjusts once an estimate is given to the block, and then it outputs the LFM as a PDU, where it labels it as an LFM and what estimates were applied to this waveform. Next up, we have how we interface with all the SDRs using the UHD block here. There's many inputs and outputs for this block. This was just for testing purposes to see how all the waveforms would turn out whenever I output them into MATLAB. And so this block controls the timing and receive times of all the waveforms, and it will control when each SDR should be able to transmit and receive. Next up, we have clock drift estimation, which is split into two blocks. First being the frequency peak estimation, which will do the FFT, the sync nonlinear least squares, and then output it as metadata pertaining to which SDR it was received by. And then once clock drift estimation detects that there's been 6 estimates done, it calculates clock drift and outputs that as clock drift estimates pertaining to which SDR it should be applied to. Following that, we have the clock bias and carrier phase estimations. And so that will be the time peak estimation block, which will do the match filtering, sync nonlinear least squares, and output the time estimates and also the phase estimates into the clock bias and carrier phase estimation block, where then we can then solve for our clock bias and carrier phase offsets for each SDR. Then the final block that I produced was the compensation block, and this is for any received waveform from the SDRs, and it will apply the phase offsets to the received waveforms to account for and help synchronize the waveforms post. Yes. And so how we experimented and validated the results were through configuring a set of 3 SDRs at X310 specifically, with an over-the-air experiment and some monopole antennas. And in the middle here, that is the parameters that I use for this experiment. And then on the right image is the setup in the anechoic chamber. And on the bottom left is a block diagram of how I laid out the whole experiment. And with that, here are the results. I conducted 2 different experiments, one with an external reference clock where I measured the performance of clock drift. And so I got into 7 and 6 parts per billion for SDR2 and SDR3, which unfortunately wasn't low enough to further estimate clock bias and carrier phase. So for the next experiment, I ran two different parameters, with one being the internal reference clock, one using the internal reference clock, and one using the external reference clock, assuming ideal clock drift estimation. And as you can see, the error rate for the internal clocks are ranging from 26 centimeters to 61 centimeters, and then for the external clock, it was able to get down to 3 to 5 centimeters, which was enough to estimate for carrier phase. And so with that, we wanted to test to see how well carrier phase did, and how we did that was by having SDR2 and SDR3 transmit to SDR1. And so the first time slot was solely SDR2, and the second one was SDR2 and SDR3 transmitting, and then the last slot was for SDR3 transmitting by itself. And from there, we were able to get a coherent gain of 98.62%. So the conclusion and future work. So I was able to implement a synchronization algorithm to an outer tree module called GR Harmonia. And then I was able to characterize the performance of the clock drift, clock bias, and carrier phase estimation, being able to reduce clock drift to 6-7 parts per billion, and also achieve a maximum of 98.62% gain and a reduced clock bias to 3 to 5 centimeters with an external clock reference. So some future work that I wanted to do was that I wanted to improve the documentation of the module so that people could understand what's going on in the blocks, and also add a UHD block that would only control one SDR so that it's more easy to look at. And then also incorporate SNR estimation, weighted least squares, and common filtering to improve the clock drift estimation so that I could further integrate it within the full algorithm and test it for later purposes. And with that, thank you for listening. Are there any questions?
Thank you, Cody. Hello? Sorry. Thank you, Cody. Any questions for Cody? One back there.
Not a very fast runner.
So the slide deck showed like drones.
Yes.
So are you expecting to continue to use this for non-static SDR sources, like moving around, or would you have to change the way you're analyzing this when they're not just like, remaining stationary?
Could you repeat that again?
Sorry. Would the technique you've highlighted here continue to work for non-stationary radios that are moving relative to one another without knowing what direction they're moving?
Yes, so actually the full algorithm can actually compensate using common filtering and estimation of the positions and the velocity of the platforms, but for now it is all for stationary platforms.
Any other questions? A couple quick questions. Did you use common filtering yet, or that's just for future use?
That is for future work, but
Could you talk about what your biggest struggle was in all that good work? Where did you fight the most?
So I definitely had a lot of struggles with learning how to do C++, learning GNU radio and Linux all at the same time. So there was definitely a learning curve, but I definitely learned a lot, which was nice.
Very good work. Okay, let's give it up for Cody, and we have about 10 minutes before the next speaker, so we'll just take a little break for 10 minutes, I think. Makes sense? Okay. Thank you, Michael.
Hi. Hello, my name is Michael Aldred. I've been part of a research project at the University of Technology, Sydney, developing acoustic communications in different materials, including steel rail track. And this presentation provides an overview of the research and explains why a preamble was needed for this flow graph. So just index and the next one. So the research objectives is to use acoustics to transmit images and other data through hard substances like railway track, shipping boxes, metal plates, etc., where RF cannot propagate. So develop an acoustic digital communications SDR-based channel in materials and overcome the difficult multipath issues which are really prevalent in steel track. The application can be used in any substance, including dense materials, concrete structures, and marine environment. The data should be complete, not repeated, or have parts missing, be able to tolerate mixed material that will have different propagation speeds, and signal arrival time at the receiver. But first we need to clarify the difference between RF and acoustic communications. So RF communications has been with us for more than a century. It's established, mature technology, and it propagates at a constant speed. And any received delay is a result of time over distance. Reflected signal has just a slightly longer delay, and in mobile communications we take advantage of that for MIMO. When RF encounters a dense material, it does slow down by a small fraction, but it's small in comparison to acoustics. For example, in the vacuum of space, RF is 300,000 kilometers a second, but in air, it's 0.9997 of that value. When it encounters other material, it does slow a little bit more, but it's still not so much. But it does get attenuated. Some of the frequencies do get attenuated, like mobile spectrum frequencies in as little as 10 centimeters of water. And your phone does not work underwater for that very reason. And acoustic communications can be used as a solution when RF communications is blocked or absorbed by dense material substances. So this is just basically traditional radio systems, which we all know and love. So what is acoustic communication? So acoustic communications can be as simple as two people talking to each other. Unlike radio communications, sound requires a physical medium to travel through, and that medium determines the speed of propagation. So in a vacuum, sound cannot exist. Space is silent, despite what the movies often suggest. Speech begins when an electrical signal from the brain triggers the larynx, causing air flowing past it to vibrate and produce sound waves. And these vibrations propagate through the air, carrying information to the listener, and then the eardrum vibrates in response, converting that back to electrical. So in a person, you basically have the vocal cords, air flowing over it, pressure wave. The person receiving that pressure wave can decode it. You get your electrical signal back, and therefore you can actually understand what's the communications that's being said. So acoustic communications travels in air at 342 meters per second. In water, it's faster at around 1,500. And the ocean, surprisingly enough, has a lot of noise in it. It's, with wave action boats and marine creatures. You can play music in water, but we can't generate audio in water because of how we are. Pressure waves in liquid that allow the sound to be transmitted can be reflected from the bottom and surface level, and it can be impacted by water current, salinity, and temperature, and this creates like multipath issues that can be difficult to demodulate. So these complex signals require a more sophisticated communication system to transmit and receive them. So acoustic communications can be used in dense and very dense material. Like in rail track, the speed of sound in rail track is about 6,000 meters per second. You can often hear things happening on the rail. If you listen to the track, you can hear the train coming a long way away. And we also use the actual track, transmitting audio through the track as part of track detection systems. So they use frequencies from 1700 hertz to 2600 hertz to actually, as part of track detection. And transmitting tones through REL is a very, it's something that's done quite a lot and has been done for many years. This is just a simple audio frequency circuit that they would have used. Again, it's transmitting tones in those tracks. So railways use RF communications for voice systems and maintenance activities, and railways are linear corridors connecting population centers. Mobile phone utilities are profit-driven, and they will not put base stations in areas where they will never get a return on their investment. And railway owners will put communications in to meet its operational requirements and cover activities that they have decided are core. And contractors doing track work, commuters on the train and residents may have to find alternative solutions for communications. So just in railway tunnels are basically generally never straight, and creating an RF link through the tunnel is not possible most of the time. And if you only need a temporary link, putting a cable in can be expensive. You may not have sufficient time to actually to do that anyway, and it can be a bit of a tripping hazard, and it can be an issue. What you really want to do is we want to be able to have an image that we can send acoustically through the railway track, so that we can have that information when we need it. So this is just a railway track that you can see there's a curve in the tunnel. So the main components to creating a digital STR channel, basic laptop, the actual software, and the transducers. And this is a functional block diagram, basically just showing the laptops. I'm using an audio device, sound card, Bellringer. It's samples at 192 kilobits per second, and because my target frequency is at 40 kilohertz, it actually works quite well. So in an RF environment, we use antennas, but in an acoustic settings, we use transducers, and the transducers that are selected depend on the modulation protocol. So if you have, for example, FSK, you would use one type of transducer, but if you're going to use OFDM, you have to use a transducer that has a more bandwidth available in the transducer. So we're just going to start off with some of the transducers that I've actually been using. So this is a general purpose transducer. It's got a 1 kilohertz spectrum. So you have to, for FSK it works beautifully, but you can't use it for anything that needs a bit more spectrum, like OFDM. Its applications, it's used pretty much in electronics and movement detection, parking sensors. But it's a cheap and useful component. I found these transducers were a bit better. They had a bit more bandwidth. And again, I had about 2.5 kilohertz, 2.5 to 3 kilohertz across the actual, before I lost the actual signal. And that was quite good. They're, again, used for echo ranging systems and for a variety of different applications. And I moved on to piezo tweeter transducers. They were also very good. They were very cheap, very inexpensive. But again, they worked surprisingly well for broadband applications for using OFDM. Again, it's within a couple of kilohertz of, so my range would have been from 42 to, from say 37 to 43. So I had about 6 kilohertz when I was using this one. So that was actually, they were quite good. So that's piezo tweeters and ceramic disc transducers. That's another type that I've actually tried. They worked quite well too. and again, lots of applications. And the last one was a bolt-on Langevin transducer, and these are all like antennas for the for RF. Only this is for acoustics, and these were quite good as well. They worked quite well. So I'll just go down to the flow graph. The flow graph slides show an original OFDM flow graph that was created last year, and there was no preamble on it. And it's using the HTML-C encoding, and you can't transmit images in this particular flow graph because there's a certain loss at the very beginning when the flow graph, when you're synchronizing your receiver, and you actually lose data. So when you want us to send an image using this particular flow graph, I'll just go into the flow graph, you can't, because the image, the first part of the image is where it has all the important information about the type of image. But for text and audio, it worked quite well. And I won't play all of this, but I'll just show you. This was one. Just sending text, so I'll just move it up to see if I can get to the point where I actually had text.
Okay, so this is.
I don't know if I can.
Okay, so this is a test.
Okay,
so this is a test.
It may not let me move up to the point I want. Not really. So I'll move past this one anyway. But this is the outcome of that particular. When I was sending the actual data through a steel rail, and basically I was missing part of the text. It was repeating all the time, and it wasn't really working out for me because I wanted to send images. Like audio is great, text is great, but there's more value in images. That's what everyone wants when you're doing this. And so there was a modification of the OFDM flow graph. With an embedded Python block that was created by Barry Dugan. And I tried the OOT block, but it didn't work out so good for me, but the embedded Python block worked well. And I was able to use the base 64 encoding, which was very good. And it does make the received file a little bit bigger, but that was still okay. And the flow graph is run off the command line and synchronizes quickly with the receiver. And the following video clip shows the transmission and received image matching the original, right? So I'll play this one. So this is the first one.
So this is going to be in two parts.
Okay, so this is going to be in two parts. I'm going to transmit this image, which is a polar bear. It's quite a big image. And I'm going to transmit it through the rail track over there. So I'm going to get this going and get another time. So that's actually started up. It's 15:34. And I'll just confirm that we've actually... So that's all good. All our data's come in, so that's all good. Everything is fine in there. So we've got data flow, and the file that we're transmitting it to is going to be out3.tmp, which is, I just want to confirm it's actually out3. So that's actually gone to 0, so that's actually gone to 0, which is good. And we'll just have a quick look around here. This is 30 kg rail track. 30 kg. 30 kg is a track, 60 kg per meter. I've got our audio device, and we've got transducers on both sides. These ones on the back aren't used; they're 48 kilohertz transducers. On this side we have the other transducer. On this side we have the other transducer. Coming around. And then we have this here. And then we have this here, as you can see. And just come back here to see the data flow is still going okay. And data flow is still there. And data flow is still there. We don't have a very good, very low signal level. It's there anyway. But it's there anyway.
So we'll just wait and see, and all right. So we'll just wait and see, and we'll come back and look at this later. And at the moment, at 3. Okay, now I did actually do this with 2 laptops, but I didn't record it. But so this was after 20 minutes. In 2 parts. Okay, so this is going to be in 2 parts. I'm going to transmit this image, which is a polar bear. It's quite a big image, and I'm going to. So it should be this. This is the. Okay, so we've let the. Software run for a bit, and now we're going to close it off. At the moment, now we're going to close it off. At the moment, we've got a file 131.1. 131.1. That will come up a little bit when I close the file. So that's become 6. It's still 131.6. Not sure if that will be enough, but let's see what happens. We're going to go to this one here to run the stripping tool. And we're going to be looking at out. And there it is. So polar bear. Yay! So that was transmitted through. So transmitted through the actual track, which is really good. And with a JPEG image, there's if you miss the bit at the very beginning, you actually lose the image entirely because you only need a very small error at the beginning of the transmission. And the JPEG file just completely, it doesn't actually build at all. So that was that one. So I'll just continue on. So this is the image that was received. It took about 20 minutes. I think I had about 2.5, 3 kilohertz of bandwidth, but using the Pro Plus transducers. And it did work out quite well. So my objective was to transmit images acoustically, and that's been achieved. The image speed is slow, but some refinements could improve this. The received image quality matches the original. It was a 100 kilobit file, and once I stripped the post and preamble, it was back to the original. There was no errors in it, even though I have had others that have had errors. So improving the software would achieve, basically automate the removal of the preamble on received files and allow FlowGraph to be run without opening the command line. And this is very useful for sensor data. You can actually, because you're not going to lose the first bit of sensor data if you're using OFDM. And you can do a bit error rate comparison by comparing the original file and the received one. That, I think, is probably a good way to actually determine what errors are in there. But it's been for what I've used it so far, it's been very good. So just acknowledgements for Barry and some people that have helped me along the way. And yeah, so that's kind of it. Thank you very much. And if there's any questions, I'll be happy to take them now.
Thank you, Michael. Any questions for Michael? I have one. What modulation were you using for your subcarrier?
So I was using OFDM.
What for each subcarrier? Was it a QPSK, 16 QAM?
I think it could have been PSK.
PSK, okay.
Yeah.
Like a low level?
Because it's the one in the actual GNU radio block.
Got it.
So.
Oh, okay, 8 PSK probably. Yeah.
So that worked out quite well.
Yeah.
But it just means that you can use instead. I know we use GNU radio for radio frequency for RF, but it means you can use it for acoustic communications as well.
And I noticed your transducers, they look like they're right opposite each other.
The transducers on the track?
For your test track.
Yeah, so I had the 2 transducers on, it was only 0.5 meter of track.
Right.
But I've done it on longer track, and I've also used 2 laptops to have them separate. But the video I made was only just with 1 laptop.
Right. And what do you estimate for that transducer you use, the range you could get?
Well, for just tones, it can go, we've actually tested for transmitting tones about 50 meters.
For that module? modulation, do you think?
But not on that. We were just right at the very beginning when I was starting my PhD. We were doing. We had access to the track at the rail management facility on one of the actual sidings, and we were able to send tones that were detectable and that were okay about 50 meters.
Mm-hmm.
So we're fairly confident that you could create a communications link that's at least 50 meters long just by putting 2 transducers on the track, one at each end, and then you can establish a link. It means that you don't have to run any additional infrastructure across that, and you can just use the track as the link. Now, Railtrack has a lot of multipath. It's got transverse and longitude waves.
Mm.
And OFDM is brilliant for actually managing received signals that have multipath. But like when you try that with FSK, it doesn't work at all.
Right.
But OFDM worked beautifully. But to transmit images, we needed to have the actual the post and preamble, and that was work that Barry Dugan did originally for the FSK modulation protocol, and that provided a lot of that worked so well. I wanted to do that with the OFDM flow graph, and as you can see, it's overcome the multipath issue, and it's overcome the issue with the beginning of the file being corrupted because you need time for the receiver to synchronize. And it means now that whether it's photos, images, or audio or text, or even sensor data, you're not going to lose any of the data in the transmission.
Great. For the tone testing you did you measure the SNR that you got at the end of 50 meters?
We did at the beginning, but that was about 6 years ago.
Okay.
Yeah, but we were able to actually get. It was detectable tones that we were getting at the time, but it's obviously there's some more work that could be done, but it works. The software works, and I think that's obviously going to be.
Nice job. Now let's give it up for Michael.
Thank you.
And Stefan, is he in the room? Yeah, we'll start in about 5 minutes or so, just because we're a little early. But if you need more time, you got it. You got a few extra minutes. So, but yeah, 5 minutes, and we'll start with Stefan. So
All right.
welcome.
Thank you, everybody, for taking the time to watch my presentation, all the wonderful work of the folks presenting before me. I sincerely hope you enjoy the PNW weather. It's pretty cool today, which is awesome. For folks watching us online, please subscribe and get off TikTok. This is important. And let's get started. So the work we're doing starts with the motivation of the group that I'm part of, which is called the Center of Smart Streetscapes, funded by National Science Foundation. And out there we focus on forging livable, safe, and inclusive communities through real-time, hyperlocal streetscape applications. We have all kinds of thrust, and we focus on sort of from low-level signal processing, localization, digital twins up to application level. And the idea is basically to sort of make better smart cities for the future. My particular topic and sort of area of interest is around data-driven decisions. And so the premise is that local governments and cities, they need to have better way to understand what's going on out there. And usually that is done through all kinds of surveying, which is really not fast and not efficient. And we want to provide them with the sort of privacy-centric kind of data to understand what's going on. For example, if you are opening a new Starbucks location, how do you know what kind of foot traffic you're dealing with before you plan and invest money? Or if you are improving sidewalks, for example, you want to understand sort of A/B test what was the traffic before and after you've invested millions of dollars into construction efforts. Now, the status quo of this effort is video surveillance, and I'm sure all of us here understand what are the downsides. Sort of privacy, right? Your faces are going to be exposed, and we don't know what kind of malicious folks are going to be using this data in the future. So that's really not great, and we'd like to find a better way to do this, and we are focusing on privacy-centric mobility intelligence. And so we want to go from I know your name, I know your phone number, which is something you can do through computer vision and through all kinds of other ways folks do this these days, to I just know that there is a dot out there. I don't care whether you watch cat videos online or what is your phone number. I just want to understand what is the trajectory you've used to go from that local Dunkin' Donuts to a local library. And I want to potentially, ideally, put some flyers in the library, maybe. So that's the kind of data we want to be able to understand. And over time, that is a fantastic data set for folks who want to improve smart cities. Now, how do we do this? Our current sort of mission, which we started about 5 years ago, is through using something called Wi-Fi probe requests, which I'm sure a lot of folks here would know. These messages, your phones, your Wi-Fi devices really emit every time you want to connect to Wi-Fi. The beauty of these things is that they are entirely passive, meaning that we can listen to them, we can set up a monitor mode and a sensor like this guy, Alpha Sniffer, and we can just continuously listen to this on various channels, or either we hop or fix on one, and we can sort of gauge how many people are there, assuming we know that they have phones and watches and stuff like that. We can sort of gauge what's going on in the public. Now the problem, and obviously we've built the sensors for this, we've deployed 54 sensors in West Palm Beach with these devices on board, Raspberry Pi, Alpha Sniffer, battery control, and basically we put them electrical poles and we try to understand this information right now. It's been about 5 years since we started, deployed 54 sensors around Clematis Street in West Palm Beach. Local government is very happy about us providing this data for them, and the important key is that we don't know who are the people. We just know that there is a certain trend of what's happening during a public event, or like we did a couple of years ago, we could easily understand what were the effects of them introducing certain COVID, for example, restrictions, right? Now, the challenge with the probe requests is that the MAC addresses on board, which is also an advantage, but MAC addresses on board of probe requests are randomized. And that's for a good reason. We don't want people to stalk you, right? But for us, considering our purpose and the fact that we really want to sort of obfuscate all kind of personally identifiable information, we still want to go around MAC address randomization if we can, because if we understand that there is this phone moving, we can understand the trajectory, and that's what we're really looking for. And the best way to do this that we sort of so far chosen to is something called RFFI, or RF-based device fingerprinting. And the idea behind this technique is that we basically want to use deep learning to extract device identifying features from the hardware that was used to emit the signal. And these impairments, these imperfections that we try to fingerprint in chipsets, they're usually introduced on the factory floor when this chip is being produced, not because it's an effort of a chip maker, but just because it's too expensive to get rid of them at scale. And really not worth it because, most of the decoding techniques would sort of deal with that. But for us, that's sort of like an advantage. There are obviously challenges. The first one being that these techniques are super sensitive to various environment changes, to micro-Doppler effects, to transceiver synchronization issues, and the fingerprints you would extract are usually device-specific, receiver-specific. So there is a lot to work on here. And the challenge with current approach to us building these models to extract fingerprints is that it's really hard to debug, right? If you go and collect a data set, spend 3 days in a facility collecting various kinds of data that you've designed to set up, and then you go and train your model and you open that Jupyter notebook, you plot your figures, how do you know how that model would react to sort of dynamic changes in the environment? What if the device moves a certain way? What if there is a bunch of interference involved, right? You want to have a sort of a rapid way to prototype and sort of hot swap these models and see if you can improve your situation. And for that, best way to do this is through GNU Radio. And so what we've done is first of all, we've built a new sensor. For this, we've used NTZR E200, super low cost, available out there. Basically it's a Pluto SDR on steroids, and it allows us to install something called Open Wi-Fi to basically be able to capture Wi-Fi signal, extract IQ samples, as well as also decode the signal on FPGA, and then be able to sort of combine the IQ samples that we capture of preambles, as well as the various data like MAC address, sequence number, PNL list, and use that later in GNU Radio to perform our fingerprinting. And I'll explain each of those steps in a second. So this is a quick setup we've so far established. On the left side there you see 12 alpha sniffers. These are playing as our emitters in this case, not receivers but emitters. They're super low cost, very easily accessible on Amazon, and they're great because you can quickly establish monitor mode and inject whatever packets you prefer. In our case, those would be probe requests that we inject ourselves through Python SDK. And we fix a MAC address on each of those so that it was always the same. We can filter out our traffic, but under the hood, of course, we expect to fingerprint without knowing what device it is. On the right side, you're going to see a Raspberry Pi controlling those alpha emitters, and also our NTSDR receiver, which is connected with an Ethernet cable to our host. So let's talk for a second about what kind of signal do we expect to hear. As I mentioned before, we focus on probe requests. These are sort of very commonly used types of frames. Each frame starts with a preamble, and the beauty of a preamble, as you know, is that it's always basically the same, and that's what we want. We want to reduce the number of variables we need to fingerprint. We always want to hear the same sequence from every emitter, and that's the best way to do this. And so our goal that we actually implement an app on the NTSDR in Rust so that it was fast, which basically captures this data, which I'll explain in a second, extracts the preamble, sends it over to the host, and later we use it for fingerprinting. Now here's how this app works. So all of our emitters are fixed on channel 36 of 5 gigahertz Wi-Fi. By the way, we could change that, just an example. The only nuance is that we can't use 2.4 gigahertz sort of channels, because on those probes are emitted with DSSS instead of OFDM, and current version of Open Wi-Fi, which is our sort of baseline how we implement this, doesn't support DSSS. So we have to focus on sort of 5 gigahertz channel, and that's kind of one of the limitations. Nevertheless, the app in Rust, which you can see to the right, has kind of small symbols, but I'll try to explain. 2 parallel processes. It first starts with the process that sort of continuously taps into the radio tab headers from the signal that is decoded on FPGA. And that is done in parallel to us reading from a DMA buffer the IQ samples from the same frames that we just decoded using FPGA. Those are being side-channeled. Then we match them, the 2 processes together, those frames, using timestamp values. And those later are filtered using a MAC address, just so that we only cared about the signal from our own emitters and not some random laptop. And then they're being streamed to the computer through a simple socket. On the computer side, on the host side, we have our GR mobile FFI set of blocks, which I'll explain in a second. Basically, the idea is that we want to be able to receive the signal, extract the fingerprints of those devices, and perform re-identification, which you can later just basically extract those fingerprints for your own debugging, or you can use one of our blocks to basically visualize the labels. Very simple, but the idea is that you can visually understand what's going on. So we start with the transformation. Now, obviously, everything starts with us receiving our PDUs. They're later transformed into a tagged stream. and upsampled. So in normal 20 megasamples per second sampling rate, you would get only 320 samples for a preamble. We upsample it to 25 megasamples per second just so that you get just a bit more signal availability for us, a quirk from previous work that we had. And then that is converted to a vector and input to our fingerprint extractor. The fingerprint extractor has a couple of important inputs. First of all, of course, you want to specify your dimensions of your data. And second, you have to provide the model that you've pre-trained. And in our case, we use Onyx so that it was sort of universal. You could convert, whether it's PyTorch or TensorFlow, you could use this. You specify your model file, and then you specify whether you want to run it on GPU, CPU, and then this model basically does the extraction. Here's how the extraction works. I'll try to be sort of high level, not to waste a lot of your time. So we take the time sort of domain signal, which our preamble, which is upsampled. We transform it to the frequency domain, which is our sort of, now it's a picture, and we like that because we use a model that extracts fingerprints from pictures. We transform it to a channel independent spectrogram, which sort of removes some of the effects of the channel in which the signal was transferred. Then there is this extractor model, which is extracting features and produces a vector that we later store in our vector database. Basically, a simple embedding, nothing special. You would see that in all kinds of LLM applications these days, just we work with signal instead of text. The next block is our re-identifier, sort of the meat of the game. It also has a couple of important inputs. Of course, you provide dimensions, and you also provide a link to your database file. In this case, we use ChromaDB for simplicity, super simple, light, great Python SDK, and it allows us to store all the embeddings and then provide the label at the end. So briefly, here's how the re-ID works. First thing we do when we receive an embedding, we run KNN search, and we provide top K candidates for our device that we've probably never seen before, or we have seen before. We'll see that in a second. And we determine what is the cosine similarity for each of those devices. The best candidate, we compare that cosine similarity value to our threshold. And the threshold is something we establish experimentally prior to running this, and it allows us to decide whether it's a known or new device. Sort of, you can use the same approach to determining whether it's a rogue device that you don't want to include in your network, but in our case, it makes that decision whether we update the fingerprint or add or enroll the device in the network as something new. If it's new, we add it to the database, create new label, return. If it's existing, we update the fingerprint, and we return an existing label. Super, super simple. Now, how does this work? I'll try to turn on this video, but that will make me get out of, okay, it doesn't actually, okay, hold up. You guys are not going to see this, but there is a video. I can sort of vocally explain what it does. Basically, there is a very small window, and as I'm launching and setting up my receiver, it produces this signal, and then you can, by the way, explore it on the website. I've uploaded this presentation too, and it's open source, so you can explore it as well. But the idea is that you can quickly see the signal and see all the labels as they are received from the end SDR, and you can dynamically explore whether the model works as well. Now, okay, let me switch. All right, so even though the focus of this presentation and our work here is not the accuracy, we still wanted to do like a preliminary evaluation of what we've produced here. And on the left side, you're going to see the same-day re-identification accuracy. Currently, it's at 94.67%. The idea how it works is that basically we enroll the devices into the vector database and then try to re-identify them 10 minutes later, 20 minutes later, and this produces this kind of high level of accuracy. But as we restart the device, introduce all kinds of offsets, and we try to re-identify the next day, the accuracy drops. So this is something we're currently working on. So there is all kinds of strategies we're considering to calibrate the receiver and to sort of fix the accuracy. And there's a couple of interesting things we're working on that will be published later this year. But that's kind of the gist. Now, this presentation for us is an opportunity to advertise this as an opportunity to collaborate, because the next steps in our journey for sort of developing this re-identification system for trajectory sort of tracking is to build a huge model which includes fingerprints and representation from most common chipsets that are available out there in the world. Currently, the model has been only trained on these alpha sniffers, which have a single chipset. and we need much more. And that's very expensive, that's very time consuming, so if anybody here would be excited or anybody watching, we'd love to hear from you, and the QR code is going to lead you directly to my email, which is probably not a good thing, but nevertheless, please use it. Another thing we're planning to work on is we want to productionalize the sensor we just built. We want to build these boxes and basically upgrade all the 54 sensors in West Palm Beach with this new ANT SDR. And instead of using Raspberry Pi, as we used to do before, we want to use an NVIDIA AGX for edge computing so that we could actually run the inference on device. Obviously, we need that for real time. Plus, we potentially might be able to run some interesting, great new experiments in the future. So that's something also to consider because this testbed is public. We can easily collaborate with you if you are curious about doing some other research out there, out in the field. So next thing is federated learning. So this one is important because, as I mentioned at the beginning, the fingerprints we extract are based on us training this model for extraction on a single receiver. Now, receivers, as well as transmitters, also have impairments. And so you get this bias, which is important to generalize away from. And to do that, it's really hard to do unless you sort of collect all the IQ samples from a bunch of sensors, bring them to the central node and do your training. Super expensive, time consuming, not the greatest way to build a production system. And so we want to work on federated learning, which is going to allow us to train on device, share the weights to the central node, and sort of improve and build these generalized models, which would allow us to, first of all, it's cheaper. Second of all, we can share the fingerprints that we extract with other receivers. So as the device is moving down the street, we saw the device on receiver 1, we can send that over to receiver number 2, which is going to make things much more efficient and much more scalable. And finally, we want to expand this beyond West Palm Beach. So we have a couple of interesting projects working currently with Columbia and so on and so forth, but if you're interested, hey, this is the best thing to do because it's going to allow us to build better towns for ourselves in a privacy-centric way, which is what all of this is about. Thank you, and I'd be happy to answer your questions.
Thank you, Stepan. Any questions for Stepan? We have an online question.
Oh, that's scary.
All right,
Someone in the world.
got one from...
Did I expose my password?
No. Let's see if I get this right. Using a KNN vector search, how do you select the number of devices? Shouldn't they be huge for a city-scale application?
Yeah. So first of all, great question. Currently, the KNN sort of is out-of-the-box solution. At the moment, this is not the priority. So we're actually just prioritizing what the ChromaDB would choose. And so I'm pretty sure it uses KNN or something sort of scaled up in terms of that. But there are various other ways to do this. But for now, we just pick top 3 devices just to make sure. But really, you could just go with one, because whatever the best distance is going to be your top K option. But it's a great question. I'm sure there are better ways to do this, which we're going to do in the future. And the beauty of this, the fact that our code is open source, is that you can actually go out there and modify it and do something better. So, and that's what we actually want to enforce, because this whole idea is that there are lots of interesting, cool potential ideas of how to do fingerprinting better. We just wanted to do this as a small example. Thank you.
Any more questions?
I'll try
Great.
one.
Yeah.
Do you have any sets, the chipsets, the Broadcom, the Realcomm, and the clones and the others, of how big that problem is? If you get like a couple, 3
Yes.
or 4?
So I've actually gone out there to ChatGPTs of the world and also Google to go and check what are the most common ones. And so I found like 5 or 6 that are used in sort of Pixels of the world and Samsungs and Galaxies. Some of them repeat, sort of use the same chipset over a couple of models like the latest iPhones. But the challenge is that, and this is my assumption, we didn't check this yet, it might not just be the chipset itself, it might be the entire RF circuit. And so an interesting thing is going to be, if it's just the chipset, we could just get like 5 or 6 devices, and that would be enough, and just test around various environments. But if it's the RF circuit, now we're in trouble, because every single iPhone, every single Android, we're up, NSF is not going to be happy. So that's a great question, and that's probably something I need to do. Now I'm a postdoc, so I'm here for a while, and that's probably going to be something I'll deal with this year. Thank you.
Anything else? Going once? We got one, yes.
We need some elevator music here.
Thank you. I would be interesting, probably I can see it in the video, but what was the environment where you have trained that and tested that. So what was the range? I assume that.
What was the,
you
sorry,
need
what?
The range of between transmitter and receiver.
Oh.
I assume that you need some SNR.
Yeah, so first of all, this was at home, and this was a very tiny distance because this was a very tiny prototype. We did some previous experiments in an orbit facility in Rutgers University that was much larger. There was like a test bed of 400 sensors, 20 by 20 meters. That was also pretty good. But I'm sure as we take this out to the streets, we're probably going to see troubles because you're moving. Your Doppler effects are going to be introducing troubles with phase synchronization and a bunch of other issues. So this was only the beginning. And yes, this data set was very simplistic, but we just wanted to make sure that it works and that we could make sure this anti-SDR device works and that the GNU radio pipeline is actually useful. But yeah, that's a very, very important thing. And we're probably going to need to train a bigger model that is generalized across various distances, SNR sort of values, various kinds of initial CFO carrier frequency offsets that sort of are randomized to some extent. So yeah, there's going to be a lot of things to generalize against. As for the device, yes, please watch the video because I'm very sad that this didn't work. But it was in Ubuntu. We trained a TensorFlow model we use Keras, very sort of straightforward vanilla Jupyter Notebook stuff. Thank you.
Okay, we only have time for about 12 more questions. So
perfect.
Any
going
other
once,
questions?
going twice.
What's that? Next, yeah. I mean, we have 12 minutes before that starts. So thank you very much.
Thank you.
Let's hear
It's
it
been
for
fun.
Stefan. Thank you. Yeah, so lightning talks will start in about 10 minutes. Oh. Oh, I messed up. Sorry. Yeah. Got it. Okay. Yeah, so lightning talks. So we got Aaron Foster is first up on the lightning talks. There's Aaron. Thank you.
Okay. All right, well, I just want to start off saying this is actually my first time at GNU Radio Conference, so I didn't want to show up empty-handed. My name is Aaron, and I'm new at EPIC. I'm an applications engineer, and there's a little backstory to what I'm going to show. I don't have any slides or anything. I'm going to do just something hands-on and in real time, so hopefully it doesn't fail. We've had a lot of questions recently at EPIC about using, well, I guess I should start. So EPIC, American-made software-defined radios. We actually have a lot of different departments within EPIC, but I had some questions recently about integrating some of our very tiny form factor software-defined radios in with various different small board computers. So people are very interested in integrating software-defined radios and everything from Raspberry Pis to other small board computers for potentially use on drones. And so I'm going to pull up a particular board here that I was sent by John Orlando, who's our CEO. He's usually at these talks. I think he actually gives talks. He couldn't make this one, so I didn't want to let him down, and I want to try and step in and show something here. So I'm on a Linux laptop, and go figure, you know, sometimes the display doesn't really work the way I want it to, which I assume this is my second screen over here. So So this board here, the Tachyon 5G, it's made by Particle. I'm not biased towards this particular board. It was just something that was sent to me by John, our CEO, and kind of jokingly, said, hey, could we get our software-defined radios running on this board? It kind of reminds me of like a Pi. I've got it sitting here in front of me. It's about the same form factor. It's kind of unique. It's got a Qualcomm chipset in it. I thought it was pretty interesting, and has a 5G backhaul on it. Has a GPU capability, which I've not really explored yet, but it has a, kind of like the Raspberry Pi 5, it has a PCIe lane that comes out, so you can integrate the various different Pi hats on top. So that kind of caught my interest there. It currently has 20.04 Ubuntu, but I just checked the forums this week, and I think 24.04 is coming out within a couple weeks. The board, or I heard somebody say something about this board is, I'm not sure when it came out, but it's still running with 20.04, but 24.04 is going to be pushed. The build that is very particular to this board will come out. This is not the easiest trying to navigate this way. So this particular SDR, the M2, the Sidekick M2, it's the one that I happen to have on hand. And I should point out, I've been up since about 4 o'clock this morning because I'm on Eastern time. And so I had nothing better to do than figure this out this morning. So the Sidekick M2 is integrated into a Raspberry Pi 5 hat that is on this board. It's a WaveShare PCI M2 hat, and it's running that SDR with a small little antenna on it. So I wanted to try and tie it into, okay, of course, GNU Radio. So I was able to get libsidekick drivers that are provided by Epic, built in such a way that the radio was seen by the Tachyon board 20.04. And then I spent, like I said, this morning, a little bit of an adventure building GNU Radio. But I just give a huge shout out to GNU Radio because it's just so, get it built across many different platforms. I had to mess with CMake and a few other things, being the 20.04 was a little bit older. But right now I have this Tachyon board. It's kind of, again, what I brought on me. I've got a USB-C cable. It's using the Android ADB connection from my laptop with SSH layered on top with a -X session in order to pull the graphical interface over to my laptop so I can just show you. So I'll just pull up GNU Radio here, and that's really kind of, where I'm going with this. I just wanted to show GNU Radio running on this platform. That's the shell into the Tachyon. You can see Particle at Tachyon there, and where I was previously running it with the Epic Sidekick. So very simple flow graph. I'm just opening it back up. I'll give it a second. Going to open up GNU Radio. Just a simple Sidekick interface. I wanted to point out too, there's Epic provides a GR Sidekick source and a SOAPy Sidekick, both of which are working fairly well here within GNU Radio 3.10.12. Again, very simple flow graph. So just added the GNU Radio, the GR Sidekick source. We've got the waterfall and the FFT sync, I think it is, that I've got up there. Again, I don't have a very good antenna. This was just thrown together with what I have. but just to show you the flexibility here. Actually can't even see the play button. I know everyone else is super familiar with play button in GNU Radio. Help me out here. Where? Thank you. It looks like you're right. So it should be starting. And I think we got to cut off the talk. It was a quick 5-minute talk, but hopefully maybe it loads up as I'm walking off the stage. But any questions, be happy to answer them or show you next door over here after the talks are done.
All right, and make sure people go check out the Epic Solution booth. You'll be there, right, to answer any other questions? All right, round of applause.
Yeah. Thank you. Thank you. All right. We next got Remington. Come on up.
Okay. Hi, I'm Remington Furman. I'm a local here. I'm an embedded firmware engineer and work on software-defined radios for the rail industry at a company called MeteorCom LLC. But today I'm presenting about a personal blog post I wrote about basic DSP fundamentals. So this is a little side project I did while taking one of Dan's classes. Let's see. All right, so the whole point of this is, the talk is for people who've looked at a correlation equation like that, a sum of the product of two sequences with a star in there, and wondered, what the heck does this mean? In short, we'll say f of n is a sequence of discrete samples of a complex vector, and it's like an input signal that we're interested in measuring properties of, and then g of n is a sequence of complex vectors that we'll use as a test signal. So when we compare the test signal to our input, we'll learn something about that, and what we'll learn is how similar they are. So the star is the complex conjugate of the test signal, and I don't have a good visualization of this in the blog, but if f of n is a single frequency, then it's a complex vector spinning around the unit circle. And then if we wanted to correlate that with itself, then we would have the test signal be the same, but when you conjugate that, it'll be spinning around the other way. So when you multiply those, when you multiply two complex vectors, you multiply the amplitudes and add the phases. When you do the complex conjugate, you negate the phase, so the phases will subtract or cancel each other out, and you'll wind up with a sum on, or product on the real axis. And then when you sum a bunch of those, you'll get a really long line off to the right, and you'll get a positive real number. And the more similar these signals are, the higher the magnitude will be. So that's the equation, that's kind of the idea, but it's really hard to visualize what that actually means. So let's get down to the visualization here. I came up with an example here where our test signal is a 3 hertz sine wave, and then what we're seeing is all those intermediate vectors in a sum of 50 samples as we sweep through a test frequency from 0 hertz to 5 or 6, maybe it goes to 10. So right now it's circling around itself, but I'm going to wait for this to restart. Okay, so it's really impossible to see this on the screen here, but as that vector, that red dot gets to the far right side of the screen, that's when our test frequency is 3 hertz, and there's a perfect match. So that was the example I was describing earlier. But when your test signal is slightly off from the input signal, then it doesn't line up, and it actually kind of curls. And how much it curls is a measure or a function of the frequency offset. And so what you'll see is that summing up those 50 vectors and that sigma above, the sum, the magnitude, that red dot, that's going to be the distance from the green dot where you're starting the sum to the final sum of the red dot. The distance between them is the magnitude of that complex vector. And so it ends up going through 0 over and over and over. So I talk about a few things to notice there. You can go to the post on my blog at remcycles.net, but the magnitude, that distance from the starting point of the sum and the final point of the sum traces out this sinc function or Dirichlet kernel. But that's where you get those scallops. Every time the sum passes through the origin 0, 0, and it sums to nothing, that's where you get those nulls. And then you can see that the side lobes there get smaller and smaller. So if we go back up to this, sorry, I have a very slow laptop. The circles that get traced as the frequency after that increases, they get smaller and smaller and smaller. It's like if you take a spring steel and wrap it around in a coil. Each time you wrap it around, the diameter is going to get smaller. So that means the maximum amplitude that you'll get when you're far away from the origin gets smaller and smaller. So that explains the decreasing amplitude of those side lobes there. And then if you look at the complex plot versus frequency, that blue line is exactly what the red dot is tracing. So the locus of points is that complex plot. So when you look at that and you look at the animation, for me at least, it helped me really understand what's going on with the math here. So that example is just with no windowing at all, the boxcar window. First let's talk about phase offset. So maybe you have the right frequency for your test signal, but your input signal is off in phase. Then the final sum won't be on the real axis anymore. It'll be at some other phase angle. So there's that example. Another one is with noise. So if you add noise to the input signal, but not the test signal, you kind of get this contorted thing. And so it doesn't exactly pass through the origin anymore. And then the rest of the post goes through some examples with windows. So what ends up happening is the first vectors in your sum and the final vectors of your sum are shorter, are in lower vector magnitude than the center part, and that's exactly what you want. You want to taper off the input on the sides. But yeah,
that's good. Thank you, Remington. Yep. That was great. Very nice. Next up, we have Philip. Philip Ballister. Yay. All right, this is our third lightning storm. It's getting rainy in here.
keep changes?
Yeah, it should have come up already.
There it's coming. See if it re-identifies. Did you do this function?
I mean, it normally just works.
Yeah. Oops. When I do that, you see that little screen? What's it say? Now do your arrow.
It works every time except for with this plug. I know, I do. Built-in display. What's the Black Magic design?
There you go. Oh, it just came up for a second. Whatever you did, there it is. Oh. It was there. There it is. It's not looking great. There it is. Yeah, it looks pretty bad. What is that? So this is a demonstration of HDMI interfaces. And what you do when it goes bad. So this is just a live demonstration of. Yes. We can go with that.
Don't touch anything. All right.
Yay.
So this is a lightning talk. I'm not going to spend a lot of time and just sort of pretend that you can see the slide, and I'm just going to talk. So I've been doing embedded stuff for a long time, and I've spent an awful lot of time creating new Linux distributions, putting them on an SD card, sticking them in a box, and seeing if it boots. And this is really annoying because I have to be in my office to do my work. And that gets old after a while. You like to run around and see the world and things. And testing is really underrated. What you'll find is manual testing is boring. So you tend to build a fairly complicated image, and you may have a couple of very simple tests you run against it, and sometimes you skip them and you don't look at it. Once upon a time, FFTW broke with a certain set of GCCs. And this showed up in a product, and that was kind of annoying. And I never really did figure out the problem, but I worked out a combination of things that worked. But the bottom line is, I let something out the door that if I had had rigorous testing, I would have caught much, much earlier and fixed and never let it out the door. If you're shipping a product for many years, you're going to have this problem. You're going to have to do updates. Let's just deal with the blinky stuff. If you want the slides afterwards, come talk to me and I'll email them to you because the last one has important links on it. If you've got to support a product over many years, you're going to have to do updates to it. Software is not a fixed thing. People are going to fix bugs. You're going to be reluctant to fix them because you're afraid of introducing other bugs. So having a good test harness around your product is a really handy thing so that you can update software and then make sure that it functions how you expect. So basically, everyone will tell you is like, don't update anything on the box because you might break what it's supposed to do. Well, meanwhile, you might have the next heartbleed bug active in your product, and you really do want to fix that, But your managers are going to tell you, I don't want to fix that because it doesn't really matter, and I don't want to break the product. So automatic testing is a really good way of making sure that you can support your product for many years in the field. So what is LabGrid? LabGrid,
I'm trying. Keep going.
all right, we have the good idea fairy. LabGrid is an open source framework based on Python for hardware testing. And you're wondering, why you might need a test framework. So many people working in the embedded space have many, many development boards running around. Excuse me while I deal with. Okay, so one thing you run into is you plug 3 or 4 development boards in. A lot of them will use USB serial cables these days, either with the adapter on the board itself or you have a separate dongle. And so you have TTY USB 1 through 4, and you can't remember which board is connected to which. LabGrid will give you a way to uniquely identify the serial adapters and then tie them to specific test instances. So you can have a set of resources tied to a specific resource. It will also let you interface with things like SD card readers, USB switches, various pieces of test equipment, Ethernet power switches, and it lets you use PyTest, which is a standardized framework, once again, standardized open source framework for writing tests. So like I said, it's basically going to let you abstract the hardware. So you basically have a test position, you have a set of resources in the test position. It will allow you to share test setup. So basically it will work in a network mode. So you can have 3 or 4 people using a test resource, and it will let you gain like shell access, so you can actually get like interactive sessions to your board farm. So what you have is a board farm in a closet, engineers at their desk. How many of you have seen the rat nest of cables on various people's desks working with embedded stuff? Yeah. This lets you put the rat nest in a closet, have complete control over it. You can have power control. You can flash the SD card remotely. And so there's no more of moving rat nests around and having things fall apart. And especially in this space, it gives you a framework to integrate things like measurement devices. So you can start automating your spectrum analyzers and things into the LabGrid framework. Please contribute this upstream. And that way you can do full end-to-end testing of your product or software. And with that, I have a slide of references. LabGrid at Read the Docs is the basic documentation. Linux Automation has a couple of pieces of hardware that are very handy for this. Unfortunately, it's a German company and they don't ship to the US. It helps to have friends who deliver you boxes at conferences. I have some sample LabGrid tests which are very basic, and I will show you them run in a minute now that Sam has fixed my video. Thank you, Sam. And there's a YouTube video that came out in the last few weeks of a couple friends of mine talking at the Embedded Linux conference about their LabGrid experience. And with that, I'm going to run the command line at the bottom. The test U-boot strategy, basically what this is going to do is power cycle the board, flash the SD card remotely, connect the SD card to a ZCU 104 sitting on my desk in Blacksburg, Virginia. It will boot it to the U-boot prompt, verify that it gets the U-boot prompt, reboot it to a shell prompt, and then go back to the U-boot prompt. And it will take about a minute to flash the card, so we're flashing the card now. And This is using a thing called a USB SD mux, and what it lets it do is it plugs into the SD card and will flip. It's going to take 1 minute, and then it's done. So I'm just trying to fill time while it copies to the SD card. This is a much smaller image than the one you saw yesterday. Do we have any questions while we wait for it to copy? It's okay if you don't have questions. I am stalling. Oh, tell a joke.
Michael has a question. Mr.
No, I
Osborne.
don't want to tell a joke on a live stream. I have a very bad sense of humor. It's also very British derived, so many people do not get my jokes.
Philip?
Yeah.
You said that the devices come from Germany and we can't get one, but you have some. How do those of us who become interested in setting up a test bed get this equipment?
Ask me off the live stream. But I'm very good friends with some of the people here, and I was in Amsterdam 2 weeks ago or 3 weeks ago for the Embedded Linux conference, and I picked up a few when I was there. So there was a complicated thing where I had to have them basically carry me a box.
But did you need that equipment?
No, you don't need the USB mux to do this. It is just really handy for a lot of the work I do if you're not constantly switching. I mean, eventually in your test setup, you're going to break it, and you're going to have to reflash the card, and you have to cycle power, and it's really annoying to go to the closet to change the card. And what you will see is I've got 3 passed. So it's basically run 3 tests and passed. And all that from my laptop here to a rat nest sitting on my desk at home. And that's it.
Excellent. Thank you very much. Okay, we have a 15-minute break, then at 3:30 it's a sponsored talk with Aronia, right? All right, so see you soon.
All right.
I'm not going to delay the break this time. I think if we can cut the live stream, Seth. Just a reminder,
talk a bit about our products which are relevant to you guys here. So primarily the spectrum analyzers and our Spectrum Echo. So to start out, Ronnie has a fairly broad product stack. I would consider us a fairly vertically integrated company. So we started out in the test and measurement area, creating spectrum analyzers primarily, but now also moved up into use cases of spectrum analyzers and software-defined radios. Primarily like counter UAS systems, think drone detection systems, counter drone systems, so jamming systems as well. Spectral surveillance, including like full trucks with all kinds of equipment, not just the single spectrum analyzer. But primarily for this talk, the spectrum analyzers are going to be of interest. On that note, the Spectrum V6 is our current line of top-end, high-end spectrum analyzers. And when I say spectrum analyzer, that's a fairly broad definition. If you go look at the actual hardware, all it really is a software-defined radio with a bunch of functions built into the FPGA fabric and into the hardware that also make it useful as a spectrum analyzer. The spectrum analyzer function specifically basically just differs from the usual operational modes that you guys know from a software-defined radio, in that the LO is swept. So you don't just stay on at a single frequency, but the LO just constantly jumps around onto different bands and collects data from different bands over time. On a side note, of course, we support Windows and Linux because we know nerds love Linux, including myself. So if you're interested in this kind of software, don't worry about it. Yeah, the main two different products which are going to be relevant here are our Spectrum V6 Plus and V6 Echo. The V6 Plus is a USB-based spectrum analyzer with up to 250 megahertz of real-time bandwidth, or potentially even 490 megahertz if you don't need the full dynamic range. So at a bit resolution, or a reduced bit resolution, you can get even more bandwidth. The frequency range that it can be used in is up to 18 gigahertz, so 150 megahertz up to 18 gigahertz for the Plus. Our newer model, the Echo, goes all the way down to 9 kilohertz. Sweep speeds for both of them are between 2 and 3 terahertz per second, and you have all the usual features like external reference clocks, GPS modules, and TCXOs or OCXOs, depending on the model. Because we are interested in the technical details here, here are some block diagrams. So specifically for the V6 Plus, as I said, these are basically software-defined radios. So you see all the typical hallmarks of a software-defined radio. So it's basically a direct IF architecture or zero IF architecture. So we don't have a super heterodyne two-stage architecture here, but just an IQ down conversion stage with the required ADCs, decimation filters, and so on. The interesting bit compared to certain other devices is probably the filter bank up here. So depending on the frequency range that you're in, different hardware filters get selected in, so you don't get aliasing over the bands. There are other features up here. So for example, we have an LNA or a switchable LNA, or actually two stages of LNAs here that can be switched in or removed. There are additional attenuators here. So we can actually deal with stronger signals as well, depending on the reference level that you set in the software. Either the LNAs are disabled or enabled, and so on. The transmit side, it looks quite similar. At least for the Plus, we have another IQ mixer to generate the passband signal, then filter banks to remove any aliases, and then finally a power amplifier. On the Echo models, the setup is pretty similar. We have our IQ mixer and the active filter bank, but there's one difference. As you might have noticed, it goes down to 9 kilohertz, which isn't actually supported directly by the transceiver device that we're using, but there is an external upconversion device in the spectrum analyzer. So using this external mixer and the appropriate filter banks, you can go down all the way into the HF bands. Same on the transmit side. There's, in this case, a down conversion filter for the transmit side, so you can go from an intermediate frequency at the transceiver that might be on the orders of yeah, 100, 200 megahertz, down-convert that into the HF band, and then output that to whatever else you have afterwards, external amplifiers or whatever. Now, I mentioned this is just a software-defined radio, so of course you can just use it as an IQ streaming radio. You set some LO frequency, and you can also just get at that data. We don't hold that data hostage, so you can use it in GNU Radio. I will also show that later. But for some people, the other modes are actually more interesting. So we have a sweeping mode as well, as mentioned. And that's why we call it a spectrum analyzer, not just a software-defined radio. In this mode, that I will show in a bit more detail in a second, the LO hops around. The other modes that we have, so the plus radio actually supports spectrum calculations on the device itself. So in the FPGA fabric, we calculate FFTs, power spectrum, all those things. There are some limitations with that though, so within the device, there's a limit to the FFT size you can use, which is also why the Echo devices don't support that feature anymore. As for sweeping, there are certain limitations when you sweep, right? Because you can't be on the whole band at the same time. So for the Echo, for example, we have a real-time bandwidth of 40 megahertz. With the plus, the real-time bandwidth is 250 megahertz. We can only look at a fairly small slice of the spectrum at the whole time, at one time, and then you stay in that area for a few hundred microseconds, for example, capturing data. After that time, you jump to the next slice. And the sweeping speed that you can achieve is ultimately limited, one, by the resolution bandwidth that you want to achieve, and by the settling times. And with the Echo unit, we have actually optimized the settling times as much as we could possibly do it to achieve the full 3 terahertz per second sweeping bandwidth, sweeping speed. For the Plus unit, even though it has much more real-time bandwidth, the settling times are a little bit worse, so you can only achieve about 2 terahertz per second, which is still fairly quick if you compare to other devices that are available. Either way, just as a side note, if you ever work with these sweeping systems, because you're not always looking at the whole spectrum, they have something, they can be described using a certain probability of intercept. So imagine you have a fairly short signal, millisecond long, couple of 100 microseconds long. That signal might appear in one of these dead times. So the white boxes are basically where you're looking at that piece of spectrum. And if you have a signal that's shorter than the time between each of these, between these windows, then you can't guarantee anymore that you will actually see that signal show up on the spectrum. And the calculations for that look roughly like this, where the sweep speed, for one, is inversely proportional to the resolution bandwidth that you want, up to a certain limit. And the probability of intercept is 100% as long as you're above the period, essentially, between these two blocks. Once you start going towards signals that are shorter than the period, the probability of intercept is reduced accordingly. So at a 3 terahertz per second sweeping speed at 6 gigahertz, to guarantee a 100% probability of intercept, you would probably need a signal of around 2 milliseconds. Usually the calculation goes the other way around. You know how long your signals are roughly going to be, and then you derive a probability of intercept from that. Now, one of the important bits, or one of the things I really want to showcase in this presentation, isn't just the hardware itself. As I said, our spectrums are essentially software-defined radios, but a very important part of that product is also the software around it. So there are actually certain similarities between our RTSA software and GNU Radio, which is how I'm going to try and introduce this. But first, the general approach to the RTSA software isn't just like with certain vendors that you have a very fixed set of features, but we also base our architecture on a signal processing graph. So just like GNU Radio, you have blocks. These blocks implement certain features, but in my opinion, the main difference between what we are doing here and GNU Radio is that the features that we implement in these blocks are on a much higher level. So, for example, if a customer wants to implement some basic spectral analysis system, they will not have to program their own blocks or build huge flow graphs. Usually a few blocks are going to be enough to implement what they need, which just keeps things a lot more manageable, but also, of course, reduces flexibility a bit compared to GNU Radio. So in GNU Radio, you can basically build arbitrary flow graphs, right? You can, depending on how much work you put into it, the possibilities are basically limitless. In this suite, application suite, we actually focus a bit more on implementing very specific use cases and applications, and trying to find a trade-off here between flexibility, so still providing this flow graph-based approach, and keeping users within what is actually supported in that application. As I mentioned, the software runs both on Windows and Linux. It's Qt-based. Quite a few of you have actually asked today. And most of the DSP is implemented on CPUs, or on the CPU. A few terminology items. So when I talk about emission in the RTSA, that is pretty much equivalent to a flow graph in GNU Radio, including the GUI layout configuration. So how in the RTSA, the GUI and the actual flow graph, so the GUI of the running application and the flow graph, are much more closely coupled than in GNU Radio, but we still have both items like in GNU Radio. So there's a separate flow graph and then the GUI that connects to that flow graph. Our streams are a bit different than those you might be used to from GNU Radio. So a stream in GNU Radio is something that doesn't have clear packet boundaries or anything. Packet boundaries are basically determined by the block that consumes a stream in GNU Radio. You can add tags, and there are ways to get around that. You can vectorize items in GNU Radio, but the basic item in a stream in our software is basically a packet with all kinds of metadata associated with it. So when was it captured? How does it relate to the stream? Which frequency was it recorded at? And so on. That provides us with some amount of flexibility, but also allows us to, for example, convey different data types within streams, and also mark those data types within the actual stream data. So you can have one connection that carries a bunch of different data types, and the receiving block can then decide based on what it actually received. It can look at the type tags, for example, and decide what to do with it. That's something that's natively supported for us. In GNU Radio, you can also do something like this, but you would have to add your own type tags or find some standardized way to do it. We also have a similar concept to the PMT messages, or message connection that GNU Radio has. So in this case, they are just passed along the ordinary connections that you draw for the streams. There's no direct distinction between a message connection and an ordinary stream connection. Now, I would like to take some time and just introduce the software in a small hands-on demo. And for a first look, this is probably, one second. There we go. So, yeah, this is what a very basic application would look like. So, I'm sorry, the screen share is messing with me a bit here. One second. Okay, that's better. All right. For a first look, here we just show a spectrum from a device that I have here and a waterfall. That's something you can easily do in GNU Radio as well. And the setup is also going to look quite similar. So we have the block graph editor included in the application right here. And when you start at the left, you have a source block like you would have in GNU Radio that represents the device that we're working with. That source block is then connected to other functions in the software. For example, something to calculate FFTs, in this case a power spectrum, so it's not just an FFT but also a absolute squared, but you get the idea. And then we show that in a histogram, in a spectrum, and a waterfall. When we go back to the actual application, up here we have the spectrum view. We can also pull the histogram up. Then down here we have the waterfall. And there we go. fairly basic use case. Things get more interesting once we start actually utilizing some of the more advanced features. So let's say we go over here. And we can see a bunch of, not sure if that's frequency hopping or just a bunch of different channels, but certainly a bunch of traffic. I made a recording earlier where there were also some LoRa transmission that I would like to pull up. Okay, so first things first. When we have an application running like this, one of the first questions is always going to be, how do I store this data? How can I record something? And that's fairly trivial, like in radio. That would be the file sync. Here we just call it a file writer. We can record data. In this case, we record IQ data. We could also record the spectral data, which would still contain information about which frequencies and all that. Just the difference is, of course, once we record spectral data, we can't really decode using that data anymore. Now, let me open up a different mission. So in this mission, I have some data that I recorded. Let me pull this up. And this recording is something where something interesting was going on. Sorry, the screen is a bit small. And I can just start replaying that. As you can see, now I don't have a device anymore. I just have my file reader where the recorded data is being read. Afterwards, I have a similar setup where I put the data into a power spectrum, generate a waterfall, generate a spectrum as well. Well, anyways, yeah, we have a waterfall, and there is some signal in there that's actually interesting. So let me try and catch this for you. Okay, I'm sorry. I will try to use this thing. Anyways, let's say I spot a transmission that I want to take a closer look at. In this case, here we have a transmission that I suspect might be LoRa. So I can start zooming into that, maybe select it, and now we can also see a frequency view down here. As you can see, it's still a bit noisy, so let me refine my selection a bit. This is also something that can, of course, be automated, but in this case, I would like to use it like the CTF player, for example, that just saw something that they want to take a look at. If you've ever used InSpectrum, that's a very similar principle. And now we can zoom into this, and that's pretty obviously a LoRa signal. We can see all the up chirps in the beginning, a couple down chirps, and then the modulated chirps at the end. Okay, different use case. So what I just did was I took a real-time, I used the device in the real-time mode, where I just have rather low bandwidth, in this case 40 megahertz, and get every single sample in that. That might not be what you want to do. The other mode that I mentioned was the sweeping mode, and I have a different mission for that one here as well. In the sweeping mode, in the flow graph that I'm showing here, the idea is to sweep all the way across from 2 gigahertz to the 6 gigahertz band, because in this case, I'm interested in the utilization of various Wi-Fi channels. And when I start this, I'm sorry, this is very cramped on that screen. We can zoom into the individual ones. So first view would be, this is our 2.4 gigahertz channel, so ISM band. So we start at 2.40 gigahertz, end up at 2.48 gigahertz, and we get a rough idea of how busy that spectrum is, what's going on. But all at the same time, we can look at the other bands as well. So up here I have the 5 gigahertz, the lower 5 gigahertz bands, the upper 5 gigahertz bands, and here the 6 gigahertz band, starting at roughly 5.8 up to 6.5 gigahertz. So for example, when we start a speed test or something that utilizes the Wi-Fi, we can actually see some activity there. Give me 1 second. So yeah, you can see that here in the 5 gigahertz band, I suddenly have a bunch of activity. and I can get rough estimates of Wi-Fi channel utilization and all the things you would do with an ordinary spectrum analyzer. So you saw the activity just got a lot stronger, which was probably because first it didn't download a downlink test and afterwards an uplink test. Yep. So that's how, or one way you could utilize the spectrum, the sweeping functionality of the spectrum analyzer. One thing to note, of course, is that now we don't have the full sample data, and for example, in this mode, we couldn't really attempt to decode any of the information, which is something we do support in the other modes. So if you're interested in a Wi-Fi channel, for example, we offer a bunch of features around Wi-Fi decoding, Wi-Fi interaction mapping. If you're interested in what's going on in your Wi-Fi network, there are quite a few features to help you on that. Now, let me get back to my presentation. Now that I've showed you some of the more basic features which you can do using our software, quite often the questions are, now how do I get the data out, for one, and how do I use my own software with these devices? So the native file format that we use is actually a custom one, just because it supports all the metadata that we have in our streams. But we provide a file conversion tool that you can use to extract all the relevant information. Like if you recorded something in an IQ stream in our format, you can use the file conversion tool to extract that information into a raw IQ file like everybody else uses. Now, for integrations, there are roughly, generally two different ways to integrate with our devices and our software. The first way that I want to show is the HTTP server, which is something that you can, it's just a block in our processing flow graph. So if I go back into the software, open this up, I open the flow graph up, I can just take any of these streams, sorry, let me make that a bit bigger, and pipe them into an HTTP server. Once that HTTP server is allocated and things are running, I can just curl or whatever tool you like that data out of the HTTP server and access the sample streams that way. So this would be useful if you actually want to use the functionality that we provide within the RTSA software, like the zoom, the sweeping capabilities, the spectrum calculations, or whatever else there is in there. So if you use the advanced features and want to extract some information after processing within the RTSA software, the HTTP server is quite an interesting option. Alternatively, if you're not interested in those features but want to remotely control the device, then that's also a compelling option. Alternatively, we also offer, oh, I'm sorry, just jumped. Native SDK integration. So under Linux, that would be just a shared library that contains all the drivers that you need to access the devices. And from there, you can just access the packet buffers directly, which of course includes a lot less overhead than running the full software. That does, of course, also mean that you don't really use the features of the software. So you wouldn't really be able to configure a full flow graph or a full graph within the RTSA software and then use the SDK. What you would do is you would just access the raw packet data off of the spectrum analyzers and go from there. A few more things about the HTTP server. Some of the more important endpoints are the remote config endpoint, so you can use that to configure a bunch of blocks or configure all the settings of all the connected blocks. Some status endpoints. There's a samples endpoint that just gives you a current, or the latest packet essentially that was streamed into the server block. So imagine you're streaming spectra information in there, and then you just want one single capture of that spectra and not a continuous stream. That will just be a huge JSON blob of samples, essentially. The stream endpoint will give you every single sample that's being streamed into the HTTP server, but that also means that you need to be a bit careful with your client. So we are talking about potentially gigabytes per second of data here, which not every HTTP library is equipped to handle. So if you're streaming a full 100 megahertz IQ stream in there, for example, curl actually doesn't really keep up anymore, and you need to potentially write a custom HTTP client that skips all the binary samples in such a way that you can still deal with the data load. Of course, your network interface also needs to handle it, but usually these things run on localhost, and the localhost interfaces are fairly efficient nowadays. This is an example of one of those sample captures. You just get a bunch of metadata, and then the sample information as JSON numbers, which of course is not going to be very efficient, but usually enough for a single capture. For streaming data, you have that same metadata as a JSON blob, but then after the metadata is the actual binary sample data, so you don't have to convert anything. As for the SDK, as I said, the integration is usually on Linux done using a shared library or just a DLL. On Windows, you get the direct access to the sample buffers and no GUI or processing graphs. As for the modes that you can use in the SDK, as I said, you don't really have too many options. Either you use the device as a receiver, as a transmitter, or a transceiver, so both receive and transmit. The other two important ones are basically raw, which removes all the resampling stages that you might still get in the IQ receiver and transmitter modes, and the sweeping mode, where it configures the LO jumping for you. So you can cover large frequency range, but of course you're only going to get spectral data there, and not something you can use to decode data. All right, so on the open source side and GNU Radio side, we provide GNU Radio integration. So we wrote some blocks that basically just utilize that SDK. The SDK implementation itself is not open source, but of course the API is. So writing open source blocks for GNU Radio is not too much of an issue. You could probably do it yourself, but of course we provide those for you. These blocks currently work with the Plus and Echo devices and will be published on GitHub. They still need they still have some bugs, so they should be published soon, but are not currently available. And I would quickly want to show you that. Of course, there's nothing too interesting going on here. We have a source block and we have a sync block, and then we can use these to stream data out of the radio. Ideally when I'm not still using it here. Okay, I'm sorry, that's a demo, and demos always go wrong. Yeah, then we go back to the presentation. All right. I would like to announce as well that we now have a distribution partner for North America. So if you're interested in one of these devices, please contact Berkeley Nucleonics, who are also present at our booth over there. Berkeley Nucleonics is a company that was founded roughly 60 years ago and has mostly specialized in test and measurement equipment for radiation detection equipment, so pulse generators, signal generators. They have delay generators and various equipment from that area, that field, scintillation detectors. Also, they do have existing spectrum analyzers, but didn't have any real-time spectrum analysis capabilities yet. So they're partnering with Aronia and will be able to provide any North American customers with Aronia parts. All right, if you have any questions, come see us at the hall, at the expo hall. I should also add, we are hiring, so if you're a DSP engineer in Germany or the EU and like writing C++ code, then come talk to us. Yeah, thank you very much.
Okay, thank you. Be sure to check out their table, Aronia. Thank you very much. Okay, next up we have John with fast FFTs on ARM using Rust FFT.
I think this is my last time getting up here. I'm sorry if it's not. All right, so we're going to be talking about FFTs and some issues that we ran into when we tried to do lots of FFTs on a little Jetson Orin device. So, my company, we work on some big systems, but I work on small systems. And so we make little handheld radios, and we're always trying to figure out how can we make them smaller, more power efficient. And we ran into some issues with our FFTs. So we're gonna figure out how we solved it. We're gonna talk about Rust, because Rust is cool. Everyone likes Rust now. So I played around with it a little bit, and I'll give you what I did, and we'll see how it worked. So we took some existing code. It worked on a server, and it worked great on the server. We were able to keep up. Put it on the little Jetson Orin NX, and it was way too slow. And things that we could do within a few seconds were taking 10 to 15 seconds. So what we found was the bottleneck was FFTW. And it was just not working near as well on ARM as it did at x86. So one of the reasons for this is SIMD registers. On our x86 processors, we have 512-bit SIMD registers. On ARM, the Neon registers are 128 bits. So that is a good chunk to come up from. But the performance hit we were seeing was worse than that. ARM devices also have lower clock rates, generally speaking, and it's a much lower power device. So we needed to figure something out. So as I was doing some research, I found a paper that made me feel very hopeful. So this was from the Air Force, and from West Point, sorry. And it was trying out the Rust FFT versus FFTW on a Raspberry Pi, which is also an ARM platform. And there's a lot of little numbers in there. It actually looks kind of blurry from here. So I'll just summarize the table from the paper and say that they found that Rust FFT was roughly 50 to 100% faster on the Raspberry Pi than it was to use FFTW. I got really excited. That sounds like it'll just solve my problem, get us back in the range of what is acceptable. So how are we writing our Rust and integrating it with our C++ and our GNU radio blocks? So the first step was to create some Rust functions. And Rust looks kind of like C++, but also kind of like a lot of languages. It's a mishmash of what the authors presumably liked from a lot of languages. So we are creating, in this case, a wrapper for a 32-bit FFT. And if you look at the top function there, this is creating a box that's kind of like a unique pointer in C++. It's a smart wrapper around a raw pointer. And I'll note that I am doing, like you can see in the free, that I'm doing an unsafe operation. When you go from Rust to C++, you kind of lose the safety guarantees and you have to do some unsafe things. So it's safe when it's in Rust, and then they don't trust me when I bring it into C++. For the execution of the FFT, I've got a pointer to a planner object and do some more unsafe operations to bring it back from C++ into Rust. And then I maybe cheat a little bit here. I pass in the plan rather than the FFT object for reasons that was a lot easier to do. But it caches the plan, so there's not a lot of cost to redoing the plan every time I do an FFT. So I got really good performance with that. The next thing that we need is to set up the cargo TOML file. TOML's kind of like YAML or JSON, but in my opinion better. And it's like an INI file, but with an actual spec behind it. So you can see here that I called this FFTR. You've got FFTW. This is the Rust FFT. And it depends on Rust FFT and real FFT. The Rust FFT only does complex FFTs, and the real adds in the ability to have real in and complex out and such. The bottom part, we're creating a Rust library, a C dynamic library as a .so, and a static library as a .a file. On Linux, I don't know what it is on Mac or Windows, I apologize. The next step is we're creating some C and C++ wrappers. So we are externing the Rust functions that allows them to be called and link against the correct library when the time comes. And then I like wrapper functions to make things easy. So I created some C++ template wrappers. I'm showing just FC32 here, but I also have FC64. There's real and complex in, so there's a lot of possibilities. So these template wrappers just do the right thing based upon the input types passed in. It's just a little more convenient to do. So with those Rust wrappers, we're able to compile the C++ code. Eventually, they were integrated into GNU radio blocks. I'm not showing that here. But at this point, I was able to see, well, what is the performance of this compared to FFTW? And so you can see on this graph, so 1.0 would mean working just as well as FFTW. Anything above that is better. And I looked at that and I thought, wow, that's really impressive, possibly unbelievably better. And it turns out that it was unbelievably better because there was a flaw in my methodology. So the fun fact I learned is FFTW has a make-based, AutoTools-based build system and a CMake-based build system. If you use CMake on anything but an ARM device, it will vectorize and use SIMD and do the right thing in there. But if you use CMake on an ARM, then it just won't do any SIMD for you. So SIMD was off, and that explained a lot of why it was running so slow. So that was frustrating. I also looked, and if you see my numbers here in the original paper, it did say that it was roughly like 50 to 100% faster, which is similar to what I'm seeing here. It is different hardware, and I didn't go and try and recreate their results. So it's possible they had a similar issue. I don't know, and I don't want to imply that there was a problem with the paper, but it did seem somewhat consistent with what I saw. So I did rebuild FFTW using the make-based system, the AutoTools, and got more realistic numbers. So what we can see is that for small powers of 2, that FFTW performs better. So we're in the maybe 0.7 to 0.8 range for the smaller powers. But for larger powers, the Rust FFT is doing quite a bit better. I didn't look into necessarily why this was happening or try and explain it, but that is interesting. And in my case, I needed a fairly large power of 2, so I was still excited. I was getting a performance improvement. It is, so there's not necessarily a silver bullet here, and every library under the sun is going to say, hey, I'm faster than FFTW because I have these 6 benchmarks that show that I'm faster, and they ignore all the ones that maybe show that they're slower. So it's somewhat of a mixed bag, but there are cases where the Rust version does a whole lot better. So that really is the extent of the talk. It was fun to play around with Rust and see how I could integrate some existing Rust code into C++. It was not a terrible Herculean effort. And for my specific use case, I was able to get a nice performance improvement, even above compiling FFTW properly. So thank you for the time. The code is, we did release the code. So it's at this GitHub address, and you guys are welcome to play around with it and use it as you see fit. And thank you for the time.
Yeah, thank you. Thank you. So any questions for John?
Yeah, I'm wondering, have you done any comparisons with FFTW3 with a properly trained wisdom file for the specific platform?
So I didn't put a ton of effort into the Wisdom training there. I did at one point. I ran I switched between the measured and the estimate, and at least on the platform, I didn't see a big difference. And that made sense to me because ARM doesn't have the multitude of options that you have on x86 to do things differently. So I didn't look into it too much, but when I did try and use Wisdom, it was the same rate. I didn't look into was I doing everything perfectly.
Yeah, I think it would make a difference in how it uses the neon stuff, but I'm not sure about that.
Yeah, it's definitely possible.
Any more questions?
Well, my experience using the Wisdom files in the KA9Q radio program is that using Wisdom correctly, and this is quoting Phil Karn, gets you about 50 to 100% improvement over not using Wisdom files. So I'm concerned about your methodology.
Okay, that's definitely a possibility, and that is something I can look into.
Yeah. Another question.
Yeah, I haven't really done a lot of Rust outside of sort of toy examples, but how does Rust handle SIMD compared to C++? Is it the same? Because like, C++ we can call, like, include blah, 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 and then we call something. Does that work that way in Rust, or how does Rust handle the SIMD?
Yeah. So SIMD support is fairly new in Rust, and so it is less mature. The Rust FFT library has a lot of, we'll say, hand-tuned SIMD routines. One thing I do really like about Rust is it does kind of a dynamic dispatch based upon your CPU like Volk does. And so in x86 there is a lot, or sorry, in C++ there can be a lot of if-defs to figure out which version of the code I should call, and Rust just automatically handles that for you, which is really convenient.
Anything else?
So I've got a question. Is this about only power of 2 sizes, or is this the more general radix with the small prime factors FFT?
Yeah, so when I saw that FFTW was doing better for the small prime factors, I didn't really look into that any further. So the Rust FFT does say that they have a lot of optimizations, and they do better for other non-power of 2 factors. That was not the problem that I was interested in, so I didn't investigate it.
Thanks.
Anyone else? Okay, well, very great talk. Thank you very much. Okay. Let's have another hand applause for John. Thank you. Next we have Jan with phase coherency, translating phase and time accuracy to the real world.
I've got lots of big people here. It's going to be fun. All right, so I'll talk about phase coherency. As you just said, huge shout outs to Eckart and Volkan helping me on preparing all that content. By the way, I'm a first GRCon presenter and visitor. So really cool event you've got set up together here. It's a nice crowd. It's a nice family. I really enjoy it. All right, but let's jump right in. A bit of an intro, what are we going to talk about? And it is really, that we're caring about multi-antenna systems, and those care about synchronization. Like, we had several talks about synchronization at NI or, Emerson or Ethos, and this is yet another one. And there's a couple of applications there, right? Beamforming is one, direction finding is one. And all of those care about the coherency between TX channels, they care about coherency between RX channels. There's some systematic phase relationship between those. But for us, it's really a question of, for all those applications, we're not the experts in applications, how accurate do they need to be? At the same time, we are designing our user piece with those applications in mind, right? So we kind of try to find out, and then we do have, this X440, for example, and does provide 8 phase coherent channels. So we actually spec that, we measure that, we try to find out how good it is, we try to optimize it for that, and get you that experience or that performance also into a specification. So does the USRP meet that need? We try to find out. And so a bit of a basics, but I won't go into all the details because they're just going to take too long. And I'd be curious who's gonna, of you has done a beamforming application, something direction finding with multiple channels already. I bet a lot of you. Just 5, 6, you're right. Okay, right. Maybe the other ones aren't anticipating they have actually done that before. But the basics are, rather simple. You put it together. We tried for the simulations we did here a linear array. So it's really just, a couple of antennas, and then they're spaced in a certain distance that is usually a relationship to the wavelength. And that stuff, you put into trigonometric equations, standard stuff. You do have a distance source, you do have planar wavefronts because all of that's super easy, right? But simulations work for that, and it actually is kind of nice to put that together. Highly recommended to do those calculations at least once in your lifetime, just to see, it's not magic. And the simulations are really, really interesting and important. When you're putting things together, then for those antennas, you actually have phase weights. So you have beam steering weights where you change the phase of each element, and with that you can tune or actually move the RF energy to a certain spot. You can receive only from that spot or from that angle, really. And so those beam steering weights you set up per element, relative to another one, sum it together, and you've got that full signal. That's all the magic there is, and that's what we're using in lots of our simulations and experiments. If you want to enhance those simulations, you gotta know what the real world is actually doing. And there's a couple of errors that you definitely, because things could go wrong, they actually do go wrong. So let's jump into those. The modeling aspect I'm using is based on a system where we're using a couple of X440s. They do have phase coherent channels, so you do have 8 of those that are really accurate, but the whole model comes from a common distribution, and then a lot of errors happen. And those errors are mostly at the up to the device based on time differences. So you take the first channel, and then all the other channels have a certain time delta. And the cabling happens, the devices itself will have some internal clocking and deviations, and so you can model all of that in time. You translate that to a phase at your RF frequency. You add cables on top of that, which also add a deviation, and then you get to the customer application plane. Now the plane there, there might be more error sources that you could or can model based on your antenna system or whatever that is, but that's really the model we're going to use. There's the way to correlate that model or add that model to the beam steering weights is pretty easy. You just have those phase deltas, for the individual elements. So that's no magic behind the scenes there. One particular important thing is because a lot of these effects are, time-based effects, so they kind of change the delay. You want to model them still in a phase. So that the simulations get easy. That helped us to understand that's not a perfect thing because it only it assumes narrowband signals, CW type signals to actually work. But that's the aspect we've used here. All right. So here's the fear pitch. Just so you know, cabling is one of the many things that you definitely in a phase coherent application want to spend a lot of time on thinking. Maybe buy the more expensive cable, and actually incorporate, certain aspects about that. One particular thing that you might have found or might have seen in literature, and here that's a publication from Huber and Zuner, is actually a so-called PTFE or Teflon knee. What that is a lot of our experiments are starting at room temperature, and room temperature is somewhere around 20 degrees Celsius. And the Teflon knee there is where the Teflon material, the dielectric, has its highest variation in phase. And so, at that room temperature, the variation in phase is actually highest. So you kind of see small deviations could make a big difference in terms of phase. The plot, if you're seeing that, is, x-axis is in temperature. And so you do have a wide temperature range, right? And it looks fairly linear, but also non-linear for that specific Teflon knee. There's also phase variation in ppm, and that's kind of your time or your phase that's inside the cable and how much that varies. If you zoom in, you basically get also the high quality cable there, and that's much better controlled. I've ran the numbers for 2 of those types of cables. From that plot extrapolated typical USOP temperature range, 0 to 55, what will happen, right? And then a minus 55 to 125, we would go to the extreme, like outside, for example. There's a certain electrical length in them, but then what you see is that PTFE-based cable actually has a lot of time variation if you're in that whole temperature range. And those 11 picoseconds might throw you off. We'll look into, is 11 picoseconds actually a good or bad number? Depends on your application, spoiler, but that's generally the thing. 3.8 degrees, some applications might like, and then there's a lot of variation if you're going high on frequency, because a lot of these are based on, the phases, for time delta actually getting more and more angular, or more and more degrees, right? So bottom line here, use proper cabling and short cabling. There's one other aspect where, usually, I would say customers or we ourselves would say, yeah, no, Jan, it's in a lab environment, that's fine. Come on, what could go wrong? It's 0 degrees Celsius deviation, maybe 1 degree, that's fine, right? It's actually much more than that. I went around with an IR camera just to find out what's going on. And it is actually, if you're not seeing that super properly, but up to 20 degrees easily in such a setup, and airflow is happening, people are moving by. So even in a lab with an AC, there is airflow, there is temperature deviation. So don't take that lightly as it's constant. It's not. The cables might matter more than you think. Right. So this is the old version of the presentation. So I have to actually show you or tell you what's in the background here. The whole slide was kind of in the PDF now getting up. So for X440 specifically, we do have a phase coherency specification, and it builds up with stability. So the kind of behind all of this, the stability numbers are there to tell you, you've set it to a certain value, and then you let it sit, and it actually wanders a bit up and down. And that phase, we've collected that over a couple of hours in the lab, and we can tell you what that deviation is over a certain time. We do have the measurement method, we do have a certain bandwidth, so all of that's in that spec. And then there's a repeatability metric, which is you reboot the device, some things change in the device, and that actually matters for that as well. So just to say that this particular device, we actually specified as stable, TX, RX, all of that stable, and that's also between devices. But we also have a repeatability, and we're not actually calling out a specific number in the repeatability, because it's actually, one of the unfortunate situations of that one is that between reboots, there's somewhere between 8 and 15 picoseconds, depending on the UHD version, that you actually get. We improved that number, but it's still a number we don't feel comfortable in terms of phase coherency, because 20 degrees is quite a lot at those high, at the highest frequency of that device. But so the error mechanism is somewhere around 10 picoseconds is maybe what you get between reboots. So we're going to use that number in simulations. I did this accuracy budget. Highly recommended to do that. I won't go into the detail for that one specifically here. But what happens is you list all the items, based on that reference, and then you have different cables, different different aspects. You come to a phi delta at the beginning or at the end, maybe a degree within a device, and then between devices might, in this particular case, be 10 degree. There's more errors, unfortunately. So I've ranted about cables enough, hopefully. Well, not enough. There's actually more, because you can bend cable, you can move cables, and that adds errors as well. So that is even more that you have to incorporate. There's some more on the distribution side, for example. If you have an Ethernet-based or GNSS-based distribution, assuming it's not right rabbit in Ethernet, you might be in the order of nanoseconds of inaccuracies. And some applications might be fine, others might not. Wide bandwidth, I mentioned that. it is actually getting you a phase deviation over your IBW. If you had like 400 megahertz of IBW, that gives you, with a certain time delta, also phase delta. And so your beam steering would look into different directions over the bandwidth. Positive side, if you're doing LO sharing, it actually helps. So that, some of the terms are actually getting less. Just keep in mind the LO distribution is kind of using a similar model. Right. Now we've looked into a couple applications and how they're impacted by phase errors. One is just do beam steering, right? And we wanted to know what the antenna pattern changes under a certain phase error. And we usually, for these, we're now using really arbitrarily high deviations that are maybe not practical for what the device is doing, just to show you the effects. And most of those times, the actual, direction is changing slightly, and then there's a few things like the nulls are moving. And so depending on your application, that might be fine, might not be fine, but so you know, it is actually changing gain, it's changing direction, and the nulls are moving. We also used one interesting thing. I mentioned, X440 has that deviation, between reboots from a device to device. So if you had that linear array, would you actually connect all of the, antennas on the left-hand side to one device, the antennas on the right-hand side on the other device? Would you rather interleave them? Maybe that's a better option. And we tried to find out, right? We knew the error mechanism. So let's see if we can exploit that, use that, or if it's a don't care. And what we found for that one is kind of a similar thing. If you're using them in blocks, you do have that direction change, and but the gain is fairly constant for this particular combination. If you're doing the interleaved one, your gain changes, but the direction is fairly constant. So depending on how you want to optimize it and what you really care about, it might be the different cabling that you actually want to do here. And then there's, again, the nulls or some of the side loops that are moving, and you might care about that as well. Right. We had another application we're trying, which is direction finding. And so that is an angle of arrival. You try to find a certain RF energy and where it's coming from. And a couple of conditions here. We're using the same arrow model, X440, just two antennas, relative spacing, like half the wavelength. And with that, unfortunately, you can't see the other PDF. So online, the other one is there. But what you're seeing that is on the left-hand side, the deviation is actually maybe a couple of degrees because it's just that 1 picosecond. So if you're using it in a single device, two antennas, it's super accurate. If you're going to the dual device, the animation would actually span across a much wider range. And so you had, I don't know, 20, 30 degree of offsets depending on that particular deviation that we've simulated for those 10 picoseconds. And so it actually starts to matter, especially in those two antenna systems, when you have such high deviations. And the 10 picoseconds, that was at 2.4 gigahertz, pretty common for a positioning use case indoors, for example. We also did triangulation. And so just think of it as, we now do 2 times the angle of arrival, but we do have, particular definitions of the positions of the devices, and then there's a definition of where the signal is coming from, and we are just modeling what the arrows are now doing to actually finding the position of C of that device. And in a single device, in that 1 picosecond case, again, for the 2.4 gigahertz, there were a couple of errors. There are, you could call them yards or meters because all of that's kind of scaling the same way. But it's, I'd say fairly accurate, but there's a certain, because of the positioning, there's a certain higher, error in y-axis than there is in x-axis. Now, if you're doing the same experiment with 10 picoseconds, or a standard deviation of 10 picoseconds actually, so it could be much wider, this is what happens. And we had an outlier here, and it was like 100 meters away, so lots of things can happen if those 10 picoseconds are there in this particular case. So just keep in mind, some of your applications might just like 100 meter away, indoor, that's the next building maybe, so that is probably too much in this particular case. We actually also tried the direction finding with the same method that we had with the beamforming, which is you steer your array in all directions and you want to find out from where the RF energy is coming. And so it's kind of trying all the beam patterns and see which one's getting the highest energy. And for that one, we also tried more elements. We tried like 4 elements, and then we actually did a 64 elements experiment, or a simulation in that particular case. And we also, on the x-axis, had really high phase deviations, but those were, uniformly random distributed. So, a particular element can have a wide error in one direction, but all of them, in average, are 0 error. It's just distributed among those antennas. And the more those antennas, or the more you've got antennas in that particular case, the more that error is spread across them, and the much lower the scaling here between the y-axis is way different, the lower the error is. And an angle of arrival estimation error for this particular case, like even at 50 degrees maximum error, was like 0.2 degrees of angle that we're off. So pretty good, which also kind of an interesting finding for me is, if you're going to more channels, it actually helps for this particular case. Another one, or another direction you can think of in applications for phase coherency is cellular communications, right? So you want to service multiple users, for example, you want to steer the beam towards them, you want to direct the RF energy to them, or their RF energy to you, so that you can just identify that particular user, and all the others are zeroed out, for example. And so in that particular application, you care about the gain, and the gain actually doesn't drop as much if you're doing difference in degree in the simulation we did. But what does happen is that your interference actually is getting substantially higher. And so if you had an interference ratio of 6 dB, that means something that is transmitting from a different direction might actually interfere with you much more, and you care about that. So your phase difference matters for that interference or the interference cancellation. And the cellular communication sometimes is not about steering the beam perfectly. It might be off by a bit, but steering the zero, the null, to a direction where other RF energy is coming from, and you want to optimize for that. And then better phase difference or better phase accuracy is super important. All right, pretty quick, doing good here. Some news, some takeaways. I'll do it this way around. We do have like a 3-step approach we've taken today, and I would highly recommend to do kind of the same thing here. If you're starting with start with the basics. It's not too hard to actually put a simulation together. That's simple models of antennas and just the geometry, and you get started really quickly. Like Eckert and Volkan did like a MATLAB and a Python simulation, and run with that a couple of days, and you've got a decent result that you can use. But your application has a different care about than others have, and so you definitely want to optimize for that, and there's no particular look this direction, look that direction. It really depends on what your application is. What's substantial to actually make those work is add errors to them, right? Make sure they're realistic, make sure they're actually, realizing if you're off, so that you don't have, expensive mistakes in the field, because it's not going to work anyways. The simulation can tell you that. But then, obviously, I'm, hardware architect of USRP, so I encourage you to go to the prototyping stage as well, which is, it adds real-world complexities, and all of them, which is antenna patterns, SNR, movement stuff is happening. So all of that's on top of each other. But if you've done your homework in simulations and error modeling, you're a really good spot to actually go to the prototyping stage. And some more here. We do have work in progress. One of the nice things about GNU radios, it actually provides a lot of easy ways to get started for doing direction finding, for example. And there's an out-of-tree module called GRDOA. We actually are currently updating our white paper of the X440 so that we can show that off to the world. And we had a white paper before with TwinRx. Now that one's getting extended to X440, which is really nice. So thanks for making things like that easy. The other ones, the product feature, we will have a timed complex multiplier that we're adding to the USRP radio block. And that can enable you, if you had those beam steering applications, you can do that in a timed way, or it would enable actually phase alignment, because most of the USRPs, we can have a phase coherency, but we wouldn't have necessarily an alignment. Your system levels on top of that, and you can use that block for your particular case. And I guess with that, is 1 picosecond too accurate? Is it not enough? Well, unfortunately, it depends. It depends on your application, so feel free to model, but also come back to us with your requirements. Super curious about that. And we're at the end, so up for questions.
Excellent, thank you. So any questions for Jan? Got one there. Let you use my mic.
Hi. The 20 degrees Celsius Teflon knee is really unfortunate, so thanks for sharing that. Do you also notice issues when you don't use a SMA torque wrench on your RF connectors?
You get all sorts of issues. The SMA torque wrench is a good one. Like if your use case is to uncable and cable again, absolutely. There will be some higher frequencies will matter as much, but or much more. There's a mismatch aspect to that torque wrench as well. And so assume you've got a long cable, both sides aren't perfectly matched. And so that means, the phase of that connection is getting different, and depending on the frequency, it might matter, it might differ a bit. So all of that's in, like, cables and connections, keep them as they are, don't let them move, ideally at a constant temperature and really high quality cables, as short as you can, and you're in a good spot.
Thanks.
Any other questions? All right, well, thank you very much, Jan.
Sure thing.
And that wraps up another good day. So just a reminder, we have the event tonight at Carlton Farm, 6 p.m. Gather for ride sharing in the front lobby between 5:30 and 5:45, and the fun will continue. Thank you.